Hi, good evening all. Hope my screen is visible. Okay.
Yes, sir. Sir,
Great.
live stream.
But yeah, live streaming actually there is a issue. The PDSA, admin login, I'm not able to log in. So I do one thing actually. After this recording is over, I try to push this one into YouTube. Okay, that's it. Okay.
Yes.
There is issue in the PDSA login. Yeah. So is it my screen visible? Hello.
Yes, sir.
Good. So listen that till now we have worked with that week four. Of course, up to that quiz one, week four is okay. But whenever week five is started, there are some more complex algorithms are introduced to the non-linear data structure. Actually, the week four itself, you are familiar with some graph algorithms, that is DFS, and components, topological sorting. All these are, non-linear data structure, which is graph. So same graphs we are working in the week five also, but some more additional properties and functionalities are added and extended. What we can do, more applications using graphs. So that is about the week five. Whenever you are moving from week four to week five, there is edge with weight is added. Earlier in the week four, the edges are just it is directed edges or undirected edges. No weight is included. But now in this particular week is the edge is available with a weight. There is a weight is added. So basically just directly jumping into the algorithm before it. So I want to show you that some of some kind of how that adjacency matrix and adjacency list it looks like for weighted graphs. So it is a weighted graph. Is my graph is visible?
Yes,
Yes,
sir.
So
sir.
good. So look at that. If you are creating uh, right, huh? Okay, yeah. So if you are creating adjacency list or adjacency matrix, if it is just simple graph is different, but there is a weight is included. Look at that. Uh, when right, the pen is this. Yeah. So this is three is a weight and one is a weight. Still, I want to reduce it. And two is a weight, and this four is a weight. So if it is undirected graph, maybe directed graph also we don't have a great difference, but only one-way connection is there, but it's a two-way connection. If this is a weighted graph is available, how this adjacency matrix it looks like? The adjacency matrix. So the matrix it contains that all kind of vertices. So total how many vertices are there in this particular graph?
Five.
Five. So that there are five rows and five columns we are creating. Let it be there. So five rows and five columns. So let it be the two more columns. Sorry, two more rows. So in this five columns also we are creating. Maybe we are making a column size is bigger. Let's see that what is there in the column. Each particular cell. This is five rows and five columns. So these are the vertices. If you consider this is 0, 1, 2, 3, and 4. Similar way 0, 1, 2, 3, and 4. So from the 0, what are the adjacent vertices are there? So what are the adjacent vertices of the 0?
1, 3, and 4.
1, 3, and 4 is there. So 0 to 0, we don't have any kind of edge and weight. So that we are just representing what? 0 and 0. Please remember there is a tuple value we are giving. What is the first 0 is? So 0 to 0, whether that edge is involved or not, that is represented the true or false. So first 0 represents the true or false. If there is edge, it is represented with 1. In the tuple first value I'm talking about this value, this value. So second value represents that weight, any weight is involved. So currently no edge, no weight. So now we are going that another, yeah. So another uh, thing, 0 to 1, is that 0 to 1 path is existed? Is it there? Is it there?
Yes, sir.
So that
Yes, sir.
true, it's a true. What is the weight involved?
3.
3.
3.
So that it is 3. So the tuple it contains like this. Similar way, 0 to 2, so we don't have anything, so that we are representing with 0 and 0. The first 0 represents that false. If instead of 0 you put it 1, it's a true. The edge is there. Similar way, 0 to 3, yes, it's there. So we are having a true here. And what is the weight there? What is the weight there?
1.
0 to 3.
7.
7.
7. Cool. So this is 7. And similar way, 0 to 4, we are having 1 and 8.
8.
So this is done. Similar way, the 2 is happened. So whatever, existing. So, but remember, a tuple is having two things. A tuple is having two things. One is that whether edges existed or not, so that it is going to be the true or false. So whenever false, we are representing with 0. Whenever edge is available, it is represented with 0. And the second value is the weight, how much weight it is involved. So if it is 0, no weight is there. So no edge is there, no weight is there. If the weight is there, definitely edge is there. So we are having some value in that. So this is called that adjacency matrix. Hope you understand.
Yes.
Is it clear?
Yes, sir.
So now we go for the same graph. If you are talking about adjacency list, so it is somewhat optimized. What we can say is it is somewhat optimized. So it is simply a dictionary. In terms of Python, it is simply a dictionary. So let it be, we are taking 0th one, a key value. So what are the adjacents it contains? It contains the adjacents of that. The first one is that 1, 3, and 4. So we are having that edge is available, 0 to 1 is there. And how much weight is available? That's a 3.
3.
Yes. So the next one is, it's called a list of tuples. What do you say that? So similar way, 0 to 3 is available, so that you are having 0 to 3. What is the weight available? It's a 7.
7.
And similar way, we are 0 to 4 is there, so we are having 4, and it's a tuple. It contains a weight of that 8. So this is somewhat optimized. Similar with the first edge, first vertex we are going. So 1 to 2 is there, 1 to 3 is there. So 1 to uh, 1 to 2. So the weight involved is 1. Similar way, 1 to 3 is available. So we are having 1 to 3. So that's a 3. And the weight involved is how much? 4.
4.
So similar way, 1 to 0 is available because it's undirected graph. Hope you know that. Is it right? 0 to 1 you consider, 1 to 0 also you need to consider, no? Am I right?
Yes, sir.
So that we are having that 1 to 0 also. So we are having 0 and the weight involved is that. So this is somewhat optimized. Why you should say that optimized is, if number of edges are 2, we are going only that list of the 2 elements only. If the number of edges are 5, we are going that list with, the dictionary list which goes with only the 5 cells. But if it is this, it is n cross n. Am I right then? Adjacency matrix.
Yes, sir.
So hope you
Sir,
understand this. Tell me.
Cross and
yes, I
Hello?
have one question.
Tell me.
Sir, in the adjacency matrix, you have
Hmm.
written 0, comma 0, 1, comma 3. My
Hmm.
question is obviously the age is not there. Means whenever 0, in between the 0 to 2, there is no
Hmm.
age. So
Hmm.
why we need first 0? Because
First 0 is
the weight
false.
will be 0. Weight will be
No,
always
that's okay.
0.
That's okay. But sometimes what happens, always we cannot say that weight is 0. Sometimes we have a edge and it might have the weight of 0. Maybe something like that.
How
Okay.
come it's possible, sir?
No, no, there is a possibility. You have that even minus value also sometimes.
Okay.
No,
Yeah,
no,
minus
actually,
will be.
no, no, 0 also there, 0 also there, minus also there. So I'll tell about that when the edges are going to be -1 even. in the lecture of the professor, he has given a good example. I'll refer that when it is okay. We have a real time scenarios. Okay. Okay.
Okay,
Then.
sir.
Fine. Yeah. So hope you understand this part of it. How that graph with weights are represented. Is it clear, everybody?
Yes, sir.
Now you see that how this is converted into digital data, because I explained you the concept. Please listen. See, just you quickly refer the code. What is happening in this particular code? So please look at here. They are taking the help of, there is direct edges they are taking. It's a direct edges graphs, means 0 to 1 edge is available, weight of 10 is there. 0 to edge is available, 2 weight is 80. 1 to 2 there is edge 6. Hope you understand what is this. Is it clear? Is it clear? Hello.
Yes, sir.
Totally the number of vertices are 7. They consider it as. So edges are given with weights and number of vertices are 7. Maybe 0 to 6 they have used it. Now they are creating a NumPy library importing, like NumPy arrays we are creating. So the NumPy arrays are very simple. We are defining just dimension, it creates. So now they are creating an array called W with all initially zeros. Is it clear that matrix is created with zeros? Is it right? Hello.
Yes, sir.
Now the shape of this particular matrix is size into size. So that size cross n into n. Is it clear?
Yes, sir.
And these two, they are using what is this, the tuple. What I said, the tuple is having, each cell is having a tuple of 2 values. Okay, so that's what they are using. The cell contains that 2 tuple value. If you specify 3 tuple value. So that is what created. Basically, it creates that a simple matrix with initially with all 0 zeros are created. Something like this. Hope you understand. Is it clear? Initially. Hello? The NumPy library will go. So hope you understand this particular statement. Okay.
Sir, could you please explain again?
Yeah, it is initially the matrix is created with all initial values of tuples of 0, something like this. Is it clear?
Yes, sir.
So that the size of the matrix is size into size. The size is nothing but 7 vertices, because right now 0 to 6 vertices are there. If you check that particular D edges list, 0 to 6 is the maximum. Totally it is 7. So size into size is created. So n cross n matrix is created. Each cell contains a 2 tuple value, initially all zeros. Is it clear? Hello?
Yes, sir.
Now,
Is it like a 3-dimensional matrix?
yeah, you can create no, it's 3 dimension. If you want to create size comma size, and then we have to specify. I think, I don't know, because basically I'm not how that NumPy array is more in deep, but right now 2-dimensional. But this is size into size, and each particular cell, it contains a 2 tuple value. Okay.
Sir,
Hmm.
from that two, one is for ages and other is for weight.
One is for either edge is available, true or false,
Okay, sir.
and second one is for weight.
Weight. Okay.
Okay. So by default, anyway, false is there, because already I said it zeros are there. No, is it clear?
Yes, sir.
Now they are executing a for loop. Please look at this for loop. Is interesting for loop. I, J, and W, because this D edges is a list of tuples. Is it right? D edges is what? List of tuples. No. Each tuple
Yes.
contains triple value. Triple value is there. The first value is source vertex, that is I. Second value is the destination, that is J. And W is nothing but weight. Okay, it's clear?
Yes.
Now, hello? Okay.
Yes, sir.
Now, the weight from I to J, that is, whatever that weighted matrix or extensive matrix you are giving, that I to J, and the 0th value we are putting is 1, because already I said it is having that W of I and J, which is cell number, row number, and column number. In that first tuple value, 0th value means first tuple value is 1, because I said it is 1 means true. Is it clear? 1 means true, no? Is it right? 1
Yes,
means
sir.
true. And then second value we are putting is the value of W. The W value means this 10, this 80, this 6, this 20, this 70, this 50, 5, and 10. These values are stored into as a second tuple value. The tuple value is having 0th index is the first index is the 0th index we are storing 1, first index we are storing weight, but remaining edges are going to be zeros, because by default the numpy it will store all zeros. Okay, is it clear? Whenever there is no edge, there is no particular weight, so that 0 0 is a default value. Okay, is it clear?
Sir,
Hmm?
can you explain that inside for loop thing?
So for loop it is taking 3 values. What is I from the DH? It's 0, no?
0,
What is J? It's 1.
1.
Is it right? Fine.
Yes.
Now W of 0th row and first column. Okay, is it clear?
Yes, sir.
In that 0th tuple value, because tuple is having 2 values. Okay. Hello? 0th row, first column. Is it clear?
Yes, sir.
0th row, first column. And
Yes.
it contains again 2 values inside, because it's a contained tuple, no?
Sir, it will contain 0, right? Every.
No, it contains the tuple value. Please consider it's an index. It's an index. It's a third index. Is it right? Hello? Hello?
Sir, why that 0 and 1 only?
So yeah, I'm talking about. See, again, I have to open my this. Yes. Yeah. See, look at here. This is I. Okay. Maybe this is I. 0 to 1. Is it right? This is I. This is J. Do you say that? Because this is J. This is I. Is it right? I to J, no?
Yes, sir.
So that I is coming here. 0 to 1. 0 to 1 means, so this particular index position of this cell is 0 and 1. Index position I'm talking about. Is it right? 0th row and first column. Is it right?
Yes, sir. Yes.
This 0th row first column, it contains a cell with 2 values. Is it right? Inside again it's a 2-dimensional.
Yes, sir.
So what is the first dimension value? 0th value. What is second dimension value? First value. Clear? How do you access tuple? How do you access a tuple? Maybe somebody, maybe you are not working that, more time on tuples. Is my terminal is visible?
Yes.
Yes, sir.
So I'm going to my Python. So I'm defining a tuple. This contains that 6, 7, and 12. So my tuple now it is 3 dimensions is there. Is it right?
Yes, sir.
Fine, very good. So now how can I access the third value? Print the third value in the tuple. Can you
T
tell
of
me?
3. T
Very
of
good.
2.
T of
P of
2.
2.
that's it. Sorry,
So
I'm
square
sorry.
bracket.
I'm sorry. Yes, square bracket. Is it clear?
Yes, sir.
Fine, that's clear, no?
Yes, sir.
Now I'm creating a list. Maybe L equal to. So I'm creating something like that is a couple of things. That is 1, 4, 5. This is first one, clear. And now second one I'm creating uh, 8, 9, and 10. So this is list of tuples. Is it clear?
Yes, sir.
Very good. Now how to access this 9? Can you tell me?
L of 1 of
L of
L of 1 of
1 of
1 of, very good.
1 of 1.
L of 1 of
1.
can you like this? Is it
Yes,
right?
sir.
Is it
Yes,
right?
sir.
Now you got the idea. Hope you understand.
Yes, sir. Understood.
So that's the thing we are doing. the ith row and jth column, again inside two values are there. 0th value is 1, first value is 3. So that's
Yes.
what they did it. So
But
0th value we are putting it is 1, first value they are putting it is weight.
sir, but
Hope you understand.
in Python we use the separate square bracket, no sir, but it is inside the same brackets.
What is that? I don't understand.
The each index will be in separate square brackets.
See here. They are getting as a tuple completely. Each edge we are getting as a tuple. Is it right? I, J, W. Is it right? Is it
Yes,
right?
sir.
So this D edges is having I, J3. So that this is okay. You are asking about comma, no? Is it right?
Yes, sir. Yes, sir.
I think we can access like this also, because it's a list. It's a list. No, it's a list of tuples. Is it right? So
Yes,
I
sir.
can access. I think so. I'm not sure. Maybe I can do it. I'm not sure about it. This is first tuple. In that first tuple, maybe I don't know whether it is. I think it's not possible. Maybe wait a minute. Something is. Yeah. Sorry. I'm sorry. I'm doing it a W. No. What is a W? It's a numpy array. Do you know that how the numpy array is created? It's a tuple of array elements. Is it right? Hello. See. Look at. I'm just doing. Just a moment. The numpy array is created as interesting way, not like our conventional list. See, I'm importing. What way it is created? Just you see that. Okay. I think it is imported or not. Yeah, it is imported. See, I'm interesting array I'm creating. It's not like lists. It's array. So I'm not making it a size. I don't know what's my size. I'm creating is a 4x4 matrix. Is it okay? 4x
Okay,
matrix.
sir.
Yeah.
Yes.
So
Yes, sir.
now print W. What way it looks like? How it looks like? Please see that. It is created something like nested lists. Hello.
Yes, sir.
So that
Yes, sir.
when it is nested list, they are using like this I, J, and then 1. Sorry, 0. I, J, and 1. So that what happens, we are calling that ith row, ith column, and inside that they are calling it is 0th value. This is the ith row, ith column, ith row, ith column. So in that they are accessing 0th and first one, 0th one, first one, 0th one, first one. So this is nested list it is creating. Of course, it's a real number it is creating. Always it is comma separator. They don't use it. They use just a dot, because that's a NumPy library we are using. Because NumPy library is very easy to create it. Of course, you can create NumPy array, and other implementation also they have shown without NumPy arrays also. You can follow that one also. This is how that your graph is converted into digital data. That representation of graph, this particular blue color graph, how you are converting into computational format, so that we can compute the algorithms. Is it clear?
Yes, sir. Yes, sir.
So now adjacency list, it is somewhat optimized. Same d edges they are taking, 7 vertices are there. Edges are these, vertices are 7. I said it's a dictionary. Please look at here. A list is a dictionary. Dictionary means key and associated with list. See, look at here. Empty dictionary with empty list is created. So that what happens, initially it creates simply a dictionary 0 with empty list, 1 with empty list initially. So that is the first for loop will do this part of it. Is it clear? The key
Yes, sir.
and empty list.
Yes, sir.
Then after that, it will do that same traversing the tuple 3 values, I and J and weight. So of course, they are using D or W. D means distance. Some graphs they call it is distance. Some graphs they call it cost. Some graphs they call it is a W. But names are different. Functionality is same. So in that, what they are doing is they try to append into the dictionary. That appending job is J and a distance value. So that's what this one is the J. This one is the This one is the J. This is J, and this is a distance. So this is J and this is distance. This is J and this is where it is inserted at ith key. This is called key. key of the dictionary. So you are appending the empty list, so that empty list is filled with all the particular values, whatever shown here. These are filled. This is creating a dictionary which is called, adjacency list. Is it clear? Is it clear?
Yes, sir.
Now the issue is directed graph is okay, because they have shown you that weighted directed graph, so that what happens, 0 to 1 there is a edge, there may not be 1 to 0. Is it right? Is it right? But whenever you come to that a undirected graph, what you supposed to do, these edges has to be double. Am I right or wrong? These edges has to be double, no? 0 to
Yes.
1 if you specify, 1 to 0 also you need to do it. Is it right? Hello?
Yes, sir.
So that what they did is, they are making a double of edges. Double of edges means another copy is created. 0 to 1 is there, no? 0 to 1, 10 it creates. 1 to 0, 10 is also created. That is done by existing D edges, already available D edges, plus they are using a list comprehension. What is the list comprehension they are using? Please look at, they are picking, this is I, this is J, they are converting J as a source, I as a destination, reverse of it. Is it clear? Second set of vertices are, edges are created, the reverse of that I to J is converted into J to I. Is it clear?
Yes, sir.
So that what happens, these edges are going to be double, they are added into this. Now this edges is having a double size of available edges. This step must be done, because undirected graphs have double directions. Implicitly they are having both directions, so you must do this step, and rest of the steps are same. Whatever rest of the steps is, what total size of the vertices are 7, numpy array they are taking, and they are creating numpy array with a tuple of elements, and they are creating this, whatever that, adjacency matrix you want to create it. If the edge is available, we are putting it true, that is one, and the cost of the edge we are putting, that's called distance, weight, all these are same thing here. Double the edges, whatever the earlier edges are, we make it double, and empty dictionary with empty list is created. After that we try to append it, J to, I to J, and what is the distance is involved or weight is involved. This is undirected graph. Whenever undirected graph they specify, you need to double the uh, adjacency edges, you need to double it. Adjacency list we have to double it, so that this part only additionally it is added, because it's undirected, no direction is involved. Up to this, is it clear? When you compare the concept with coding implementation, is it clear?
Yes, sir.
Okay, this is how basically you will convert your graph representation into digital format. The digital format means maybe in adjacency list format or adjacency matrix format. Now the algorithms are started. What algorithms or standard algorithms are involved for weighted graphs, the graph with weights? So let it be that we quickly talk about that DFS and BFS. Whenever we talk about that depth first search, we try to use maximum length. Maximum length in the sense, we try to count that number of edges, like A to B, B to C, C to D. It's going as a depth, and we are counting number of unique paths, number of minimum shortest vertices we want to cover it. And if you go for topological sorting, we call it as, how much time we are completing this particular number of tasks. Always number of tasks in the sense, either we are counting that edges counting, we are counting the vertices counting. Am I right? In the DFS or BFS? Is it clear?
Yes.
Now, edges is not a matter. We don't count the edges. We don't count that vertices also. The path means we are counting that weight, the cost, the length involved. For example, even if you want to travel from Delhi to Madras, maybe Delhi to Chennai, there are two different airway tickets are there. The first ticket is a direct ticket, which is Delhi to Chennai, which is cost around that 6,000. But there is another flight is there. You have a one break journey, that's Delhi to maybe Bangalore to Chennai. So that is cost around 4,000 only. So we don't think about that uh, number of stops, but we are thinking about that the cost involved in it, because we want to optimize our cost. The fare, the ticket price, I want to optimize it. I'm too economical. So then I will choose that even it's a break journey is there. I don't mind. I will choose that the path of that. So Delhi to Bangalore, Bangalore to Chennai. So that is called, we are identifying that the length or cost or weight is involved. That is the things which you are trying to solve in the week 5. Is it clear? We don't consider the distance in terms of the edges and vertices. We are counting that shortest paths in terms of the weights, edge weights. Is it clear there? Is it clear? Hello? Am I in the call?
Yes, sir.
Now, the first category of shortest path algorithms is Dijkstra's and Belmont-Ford. Just I'm giving you just what it is, and then we'll jump into the concept. Now let you see that the Dijkstra's algorithm, Belmont-Ford algorithm, both are used to identify the shortest path from a single source. The source is not changed. Always we have a single source only. From that source to other vertices, what are the different shortest ways are there? We are trying to identify. But two algorithms are there because Dijkstra's it has some limitations. Belmont-Ford can overcome that limitation. Let you see that the Dijkstra's have a limitations. It's a single source shortest path. Always source is only one. You fix any source. Always we try to traverse from that particular source, or we want to travel from that source. So always these two algorithms are okay, but Dijkstra's is a single source shortest one. It always have the same source or single source. It's a weighted graph. Make sure that's mandate. We cannot execute this algorithm on simple graphs. The graph with weight must be there. And it is more important. It works on non-negative weights only. If it is a negative weight is involved, Dijkstra's may not solve your problem. May not. Maybe sometimes it works also. We have that kind of scenario, but that is not discussed. But I will tell you why we are using a negative weights, because even if you just quickly you recap that Professor Mathavan's lecture, he said there is a cab driver. At the end of the day, he completes his all tourist of particular passengers and all over. He is on the way to go home. So while he's going on the way to home, he's not picking any of the passenger. Then there is a consumption of oil. So it results that a negative weight. Is it right? Because there is a consumption of oil is there, no? Is it right? Petrol. Is it right? Hello.
Yes, sir.
Yes, sir.
Similar way, there is another scenario if you consider. We have a a sales, or we are trying to do one product production department. We are producing the various items and we are distributing the different distribution centers all over the India. But every time when we are dispatching the products to different branches at different places, one particular branch is there. Always they are taking the products and they are returning the products after the expiry date, because they are not meeting their sales and they are not meeting their demand. They are ordering the huge items from us and we are delivering, but after expiry date they are returning back to us. So what happens that it results that the product is expired. So it will give you that loss instead of profit. Is it right? So that is called non-negative weights. Somebody asked about zero. There is a possibility of zero also, because we are trying to travel from maybe one place to another place. Sometimes there is a tourist packages. If you book for this particular tourist package, you get this particular one is a free. So at that time, the edge weight is going to be zero. Maybe you have. So these are different scenarios. So that's the reason. But Dijkstra's algorithm doesn't work for negative weights. That is a blind rule. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
Now it is working under the
Sir, can
greedy.
you repeat
Yes,
what was the blind rule?
blind rule. Yeah. So Dijkstra's algorithm always graph is having positive weights only. We don't have negative weights. Is it clear? This
Okay.
algorithm doesn't work on negative weights. I will show you how it doesn't work, is just because we have some kind of explanation. One example also it's there. Now it works on the greedy algorithm. The greedy algorithm is simple. What happens, it always chooses current vertex to neighbors or adjacents, which is that small distance is there, that one it will choose. Small distance. For example, we are trying to do that 0th vertex to first vertex, which is the weight of 2, 0th vertex to second vertex, which is the weight of 1. We choose the second vertex only, we don't choose the first one, because it always chooses that, which is that out of that n number of adjacent vertices, it will choose the smallest one. That is called greedy. It is always tries to choose that optimized value nearby to it. Optimized means maybe minimum or maybe maximum, but always shortest means always we are choosing minimum only. That's what they clear it is smallest distance only it will select. That's what we call it as greedy. So the next one is that optimal structure property. See, the solution is obtained with different sub problems we are combining. So actually, the earlier sub problem is that we are trying to combine with the current problem, and then because you will see the matrix how I am updating. So that updating itself, you will understand how really this algorithm works, because practically still I am not implemented. And the last one is disconnected graphs also it works, but some of them are not reachable. See, I want to tell you one disconnected graph. So please look at here. Just a minute. Yes. So here, this is we have a graph like this. We have 5, 6, and 7. Do you know that all these 0 to 6 are belongs to same graph? It's the same graph. Am I right? Am I right?
Yes, sir.
But these are disconnected component. This is disconnected component. Disconnected. This is disconnected. Even disconnected graphs also it works. But what happens, first time you need to choose this source. Next time you need to choose this source. Any of the source you have to change it. Otherwise, what happens, 0 to 3 is reachable, 0 to 1 is reachable, 0 to 2 is reachable. Are you able to reach 0 to 5?
No.
So there is no reachability. So that whenever there is no reachability to this, we have to have a new source here. The source we change it. Another source we select. Then same Dijkstra's algorithm we run second time. So we get that shortest path. So that even it works for that disconnected graph, but source has to be changed. That is only thing. Is it clear? Is it clear? Hello.
Yes, sir.
So that's what. So Dijkstra's algorithm can handle disconnected data, but it will only find the shortest path for the connected component containing the source vertex. Which source vertex you have chosen it, that particular component shortest only it will choose it. Again, if you change the source, it works. So this is a theoretical thing how the Dijkstra's concept and criteria and involved for Dijkstra's. Is it clear then? Shall we work with the algorithm? Shall we? Hello.
Yes, sir.
So
Yes, sir.
look at, I'm taking the same, see, I'm not going for the code because understanding the code is a very easiest job. It's like a cakewalk. I'm trying to show that how Dijkstra's works for this particular graph. Same graph I'm taking here, same graph, but of course it is just minimized to make you to quickly to solve this one. How the Dijkstra's works? It's very simple. What happens, it will create one particular, you know, vertex matrix, or what you can say, a simple kind of a list. What you say that. So initially, this is out of all this, they might select this is going to be source. This is going to be source. First, I'm using a black color. Later, I will change the colors based on the each particular one. So whenever you start from this source, maybe you need to work it out. All these are, how many vertices are there? How many vertices are there?
7.
7.
7. So let it be that we are having a list like this: 0, 1, 2, 3, 4, 5, 6. So let it be that I'm creating a list. Of course, maybe list is updated very frequently. So let you see how it is updated. Initially, this list contains what it contains is infinite, because I don't know how do I reach that 5, how do I reach that 6 from 0, because 0 is the source, so its reachability is 0, because I considered that source vertex means I am at the same place of source. You are standing in the source airport. What is its distance? It's 0. Is it right? Is it right? Is it right? Hello.
Yes, sir.
Yes, sir.
So that rest of them are infinite, because we don't know right now whether I'm able to reach for these or not.
Sir, if there are two sources, then we need to put two sources as 0, sir.
No, no. Wait. Please tell me what is that you are asking about.
If
Pardon.
it is two separate components in the graph,
Ah,
then there will be
we,
two sources, right, sir?
yeah. If you fix that second vertex is a source, you start from 0 here. The distance of the two is 0. Clear?
Okay, sir.
So this is done at first time. Maybe initially. What do you call this one is initially. Now let we are applying from 0. So I'm changing the color. This is the first attempt we have done it, or 0th attempt we did it. Maybe this is 0th attempt. So now we are going for the next attempt. Next attempt is the first attempt. In the first attempt, what you do is, please look at here, 0 to 1 and 0 to 2. Two adjacents are there. Is it right? Two adjacents are there, no?
Yes,
Yes.
sir.
Whenever 0 to 1, 0 to 8 is there, so we are trying to choose that 0 to 1. What is the distance in 1?
10.
10.
0 plus 10, 10. 10, is it less than infinite?
Yes.
So what we do is, we'll remove this infinite and we are updating 10. From 0, by traveling this 10 distance, the reachability for the 1 is 10. So that is updated. So 10 is updated. Next one, 0 to this 2, 0 to this 2. So already infinite is there. 0 plus this 80, how much?
80.
Is it less than infinite?
Yes.
So that it
Yes.
is updated with 80. So we got it as 80. So then after it, rest of them, so whatever the rest of them that available in this, we are not knowing, because we have started from 0 and we went up to that the adjacents of this 0, that is 1 and 2, we have done it. Now that second time we are running one more time. In this one more time, what you do is, yes, so 0 to 10 it is 1, it's okay. Now 1 to 4, we are, because we are having a direction. What is the distance? Already 10 we reached it. 10 plus 20, how much?
30.
30. Is it less than infinite?
Yes.
Is it less than infinite or not?
Yes, sir.
Yes, it is.
So that it is happened. So 30. So that 0 to 4 reachability is 0 to 1, 1 to 4, it's a 30. So this is okay, but don't worry about the remaining things. We'll update very soon. So 0 to 4, we are going at as 30. Now, so 0 to 1 and 1 to 2, there is adjacency. Is it there?
Yes, sir.
So here 0 to 1 is 10, 1 to 2 is 6. How much it is? 16. Is it 16 or not?
Yes, sir.
Yes, sir.
So here,
Yes, sir.
does the 16 is less than 80?
Yes, sir.
Yes.
I'm sorry, I should change the color. So that here, this 80 will go, 16 will come. So what happened, here the interesting fact is happened. Earlier 80 will go, this 16 will come. Because if you come directly from 0 to 2, it's 80. If you come indirectly, that is 0 to 1, 1 to 2, it is 60. You are choosing optimized path, no? Is it right? Is it
Yes,
right?
sir.
So of course,
Yes, sir.
this 30 also updated just now. I'm making it as green color. So this 0 is as it is. Yes. So now we have done it. Still we are going 0 to 1. I think there is no change. There is no indirect path. Only direct path is there. So that is 10 is as it is. Am I right? Am I right?
Yes, sir.
Now, so now the next one is, so up to 2 we went for it. So that rest of them we are not going for another level. So this is as it is, this is as it is, this is as it is. Now we are going for, sorry, one more color I'm going. This is third. We are running that third iteration. Of course, maybe I'll go with some more iterations. So now we are going. So this 0 to 1, okay. So 1 to 2, okay, because 2 is having no more. 2 to 4 is not there, because up to this, if it is 2 to 4, again another direction we'll try. So no other way. Now we are going 2 to 3. It's already up to 2, it is 16, it's there, no? Is it there? 16 is there?
Yes,
Yes,
sir.
sir.
16 plus this 70, how much is there?
86.
86.
86.
86. The reachability for this particular 3 is 86. Because infinitive is there, go off, 86 is updated. So only one way, 0 to 2, and this way we went it. Okay, so this 86 it came, fine, the reachability of it. Directly if you go that 0 to 80 and then it is not optimized. 0 to 1, 1 to 2, 2 to 3 is 86 because it's optimized. Is it clear? Is it clear?
Yes,
Sir,
sir.
sir,
Tell me.
in the second iteration means
Hmm.
a second time,
Hmm.
it should be 0 to 3. It should be 80 plus 70 means
Wait.
1.
0 to 3. See, we are going level by level. First 0th adjacents are
Yeah.
finished. Next 1 adjacents are finished. Then 2 adjacents are finished. Is it clear? We are
Yes,
going
sir.
level by level, no? Each
Yeah, in the
iteration we are going
second
level.
level.
This is 0th level. 0th level is all
Yes.
infinite. We went for the 1.
Yes.
So 0th and 1.
Yes.
This is called as 0 to 1. What you call 0 adjacents we are processing. 0 adjacents are only 2. That is this 10 and 80. Am I right?
Yes. Yes.
So
Got it,
now
sir.
we are going that from. So this is 1 because it is initial. Sorry, what you call this is initial. I should say that. Maybe I forgot it is writing of that. Initially is not included in this particular matrix. Okay. Okay. Yeah. So now this 86 is updated. This 2 after that 2 86 is done. From this 2 no more adjacents. Is it right? From this 2 there is no more adjacents. No more
Yes,
adjacents.
sir.
So that rest of them it looks like as it is. 16, 30, infinite. Now we are going for another level. So another level means from the 4 we are going. From the 4, maybe it is called, it is in fourth one. So of course it is 3 is not having further. If 3 is having further, We'll go from the 3, but we are not having anything, no. So from the 4 we are going. From the 4 we are going means 4 to 5. Already 30 is there. Is it there? The reachability to the 4 is 30. Is it right?
Yes.
So that
Yes, sir.
so that 30 plus 50, how much?
80.
80.
80. So this infinite will go. So that I'll go with some other color. Maybe it is red color or some other color. Maybe I'm using some other color. Yes. So this part will go off. This will come 80. So that fifth vertex is going to the reachability is 80. So still 4 is having another adjacent. What is another adjacent? 4
4
is
to
having
6.
4 to 6 is there. So 4 to 6 first let us be updated. So already 4 reachability is 30. 30 plus 5. 30 plus 5, it's a 35. So 35 is smaller than infinite. So 35 is updated. So that sixth vertex, sorry, fourth one, sorry. Here it is 80 has to be updated for 5, no? So this 80 has to be updated for 5. Is it right?
Yes.
So now the sixth one is updated with, so this is 80, 30 plus 5, 35. So this is updated with 35. So rest of them, any change through 5 if you go, because 5 also there, one more cycle we should run it, because maybe from the 5 we are getting some optimized value. Let me check it one more time, because fifth one also having some adjacency. Through 5 if you come, already 80 is there. 80 plus 10, how much?
90.
90. Is it less than 35?
No.
So that
No, sir.
earlier values are added. So please remember these values. Let you see that what is our code. It is getting values 0, 10, 16, 86, 30, and this 35. What does it mean? So it's simply 0 to 1 reachability is with distance of or cost of 10 rupees. Similar way, 0 to 2 reachability is 16. 0 to 3 is 86. The cost it takes 86 rupees. 0 to 4, the reachability is the last values. I'm considering the last value. 0 to 4, the reachability is 30. 0 to 5, the reachability is 80 because you required 80 rupees. 0 to 6, reachability is how much? It's 35. So this is always one source. From the source to all other vertices, how much the minimum cost or shortest path, we try to use that optimized path. So please look at the code, just what they have implemented. So see, if you have two implementations, adjacency matrix they are using, adjacency list they are using. Always we try to look at that adjacency list only, because adjacency list is very easy. The dictionary has optimized lines. We'll compare with that one only. This is adjacency list. Are you able to see the code? Hello?
Yes,
Hello?
sir.
See, look at, I'm explaining you. How do you get the infinite value? See, look at what they did, the infinite value, no? So please see this infinite value. The length of the keys. Length of the keys means how many number of vertices are there. Am I right? Because it is adjacency list means it is a dictionary, Is it right? Is it right or wrong?
Yes.
So how many vertices are there? That vertices length you are taking plus 1 you are taking. And we are getting maximum weight inside that your particular, and in the particular what is the adjacency list. What is the maximum weight is there in this particular graph? Can you tell me?
86.
80.
No, don't talk about this calculated value. Edge weight I'm talking.
80.
See, look at, because why it is edge weight, no? Please look at this list comprehension, interesting list comprehension. What they did, they are taking D only, the distance value only they are taking. That is per U of the keys. Each key we are getting, that is a U. That is from the V. So V2, that list we are taking in the U. In that case, we are taking each particular distance. You are creating a distances list. Distances list means 10, 80, 20, 6, 70, 50, 5, 10. Out of all this, what is the maximum?
70.
No, 80, no. See, please look at what is the maximum weight is there. Here is the
80.
maximum weight,
Yes,
80.
80.
Is it right? So this 80 they are taking, that is a maximum value. What is the weight is the maximum is there. That is multiplied with number of vertices. How many number of vertices are there? 7.
7.
7 into 80, if you are calculating, some value you are getting. Is it right? Is it right?
Yes, sir.
5, 6.
That plus 1 they did it, so that there is no possibility so more than this maximum. Is it right? Is it right? Even each vertex is having 80 weight, there is no chance of 81, no? Is it right?
Yes,
That
sir.
is infinite, that is infinite value that is. But thing is, either this one you can use it. Python is having, there is a defining of float infinite. There is a float function is there. Could you please check that any Google or something how to write an infinite in Python? I think this is one function is there. Just you Google it, because even I don't remember the complete syntax of it.
Yes,
That
sir.
is
It's float
that is another way.
string in INF.
You can create directly INF values, the constants of infinites we can create. Either that way I can use it, either this way I can use it. Of course, this is a complex way. I think earlier code maybe some, yeah, here it is. I don't know, this is also wrong. Somewhere we found that some infinite defined. Just a minute, because we are not, yeah, somewhere even they have used it float infinite or something. I'm not sure, because somewhere there. Yeah, here it is. Please look at here. This you can use it now. So instead of doing all the stuff like multiplying, writing a list comprehension, directly you define a constant called infinite. This is very easy. You can write instead of this bigger comprehension, you can write like this. This line. This line you can replace it. Yeah, this one instead of this. Is it okay? Hope you understand. Okay. Hello.
Yes, sir.
Now there is two dictionaries they are creating. That is visited dictionary and distance dictionary. Initially, visited dictionary, what it contains is false, and distance dictionary, what it contains, all are infinite values, because we don't know each vertex reachability, because already initially starting I did all of them are infinite. Am I right? All of them infinite, no?
Yes, sir.
So that's what they did it. Now source vertex they fixed is 0. Somebody asked it, sir, if I want to start the source is 2. Yes, you can. You can fix here source is instead of 0, you can fix 2. Maybe you can fix 2. No worries. Where you want to start that Dijkstra's algorithm, which place you want to start your travel as a particular person, which particular, either 0th one, first one, second one, you choose your own, no problem. Now computing the distance. So in this computing the distance, the most important thing is very simple constant formula. So what is the constant formula, or what you can say, a simple kind of formula, what you can say. So this formula is very simple. See, of course, code implementation is a simple implementation, but easy understanding to remember forever. If the distance of u, vertex u, plus the edge from u to v is less than distance of v, then what you do is we'll update the reachability for the v is already available distance of u plus the edge weight from u to, sorry, this is a tuple, u to v. See, I will tell you what is this formula is. So are you finding this is a source or this is a source, anything you choose it, let it be, you are considering this is a u. Do you say it's a u? Is it right? Hello? Hello? Can you consider this a u? Am I in the call?
Yes, sir.
This is a v. Can you consider this a v? The reachability from u to v, I want to find out the shortest. Is it right? Is it
Yes,
right?
sir.
Now,
Yes.
what we do is the existing distance. What is the existing distance? 0. Plus, what is the value? It is 10. The weight available to reach from u to v, what is the weight available? It's a 10. Is it right?
Yes, sir.
So that 0 plus 10, this is 0 plus 10, this is existing one plus 10. Is it less than available reachability of distance of v? What is the available distance? It's infinite, no? Is it right?
Yes, sir.
So this is infinite. This is infinite. When this is less, when this is higher, what I do is we are updating this distance of v is with combination of 0 plus 10. So that's what we have updated. Otherwise, what happens, we stay with same value. For example, if you consider this one, 6 is there. This is u. This is v. Is it right? Is it right?
Yes, sir.
So if you consider this is u and this is v, oh sorry, I'm sorry, this is already calculated. Okay, maybe something like it is 35 is calculated. We don't worry about it. But we are considering this. What I do is this distance of u already calculated is 30. Is it right? 30, no?
Yes, sir.
Or not? Already distance of u reached is 30. This 30 plus this particular one, maybe it is 5. Okay, is it right? 35.
Yes.
So that this distance is 5. So available thing maybe infinite is there. We are updating 35 is no problem. Hope you understand. Okay. Hello. Hello.
Yes, sir.
But
Yes, sir.
whenever you consider this is a u and this is a v, now you check the condition. What is the available distance? So already u is available with 80, added with 5, sorry, added with 10. Is it right? 10, no? Added
Yes,
with
sir.
10. This 90, is it less than 35?
No, sir.
So then we don't do this step. So that is what the calculation they are doing here is. Please look at here. Yeah. If the particular vertex is not visited and they are checking a condition, what is this condition? Please check it. So here u and v, I said it, no, they said it is next to v and v. Maybe variable names they change it is their own choice. I don't mind anything they use it is. Next to what should be visited? Already visited plus next to what should be visited. Already visited is this. Next to be visited is this. If existing distance, if this particular existing distance plus new distance is adding is less than the reaching, then we are updating these two sum. So what is this d is simple. We are getting that what is that the particular weighted adjacency matrix is there, no? From that we are getting two values, the tuple values, that is vertex and as well as the distance. To reach the particular vertex, how much distance is required. So here you see that there is an outer loop is available, there is an inner loop is available. What is this outer loop? To complete that, each particular cycle, I said it is different cycles, no? 0th time, first time, second time, third time. How many number of vertices are there? That number of times you need to repeat the cycles. Am I right or wrong? Because I've shown you different colors. These colors I've shown, no? Is it right?
Yes, sir.
So that is repeated by this outer loop. So that this outer loop, what it will do is compute the shortest distance to each vertex from the source. From the source, first version is updated. From the source, second version is updated. From the source, third version is updated. That is done for all vertices. And here, every time what we are doing is, so find the minimum edge center. I said the 0 is connected with 1, 0 is connected with 2. Whichever first visited is, first one is visited. That's what we are selecting, the minimum distance one. What you are selecting? Minimum distance. Find the minimum distance value in the vertices which are not visited. To the 0, whatever connected, so which are adjacents are there, we are selecting the minimum one. First we try to finish the minimum one. And the next one is, from that, what are next to be visited? See, look at here. Not visited and distance is equal to the minimum distance. That we are marking as visited. So we are marking as next visited is true. We are making it as true, true, true. So already making visited matrix true, true is already, in DFS and BFS algorithm, because already dictionary how it is updated. Am I right? If it is not reachable, we make it false. No, initially all of them are false. Is it right?
Yes, sir.
So that completely we are getting the output is this. Of course, they are not printing. So if they will return distance matrix and visited matrix also, what you will get it is here. Generally, what you will get it, another output, what you get it is, if along with distance we are printing, visited matrix also, you are getting like this: 0, true, 1, true, because already you have worked with BFS and DFS algorithms. Is it right? It's like this only, no? Am I right?
Yes, sir.
So now see this: 0 to 0 is 10. Sorry, 0. 0 to 1 is 10 reachability, because already I've shown you that whatever the values. 0 to 2 reachability is 16. 0 to 3 is 86. 0 to 4 is 30. Just you check it whether my calculation is right or wrong. Yes. 0 to 4 is 30. Yes. 0 to 5 is 80. Yes, it is that. 0 to 5 is 80. 0 to 6 is 35. This is what. So what we have done is same graph we have taken, the approach we have explained, the coding how it is implemented. But thing is, we never asked you that OPP question, something like, please write the Dijkstra's algorithm. Even you can check it previous OPP examination questions. We make a story. What story? Just like a salesperson wants to travel different cities from a city 0. So to travel that each city, he has to do some kind of expenditure. Maybe 100 rupees, 200 rupees, something like a fare. So he wants to choose a shortest path from this living city to all other cities with minimum cost for each city. So try to find that shortest path for it. So each particular path is having some weight or fare or ticket price or something like that. So then you have to implement the same algorithm, but they don't ask you directly straightforward question like do with Dijkstra's algorithm. So then you have to think, oh, I have to use it Dijkstra's algorithm. Hope it's clear. Is it clear? Is it clear? Hello?
Yes, sir.
Now, here the issue will come. Dijkstra's algorithm is not suitable for negative weights. Is it right? That's what the condition they have given here.
Yes, sir.
So because it will compute only one time, it will come to a conclusion, okay, this is the final weight. Why it is not suitable for negative weights is, we may or may not get accurate values. We are not sure. Because if you run again this Dijkstra's algorithm, we will get a different value. So that is the disadvantage. Even you can see that. Just a moment. I'm stopping this. Yeah. So the theoretical things they are talking about it. So Dijkstra's algorithm can only use it with graph with non-negative weights is there. If a graph contains negative path, negative weight, negative cost, negative length, the edge is negative. Then you choose the Bellman fold. What interesting thing the Bellman fold is, it will detect that negative weights and negative cycles also detect. I'll show you what is a negative cycle, don't worry about it. Negative cycle. Negative cycle means it will report that the values are not stabilized. It will say that the values are not stabilized. So maybe it contains that negative cycles are involved. So that if the particular graph is given with any negative weights, you say that it is definitely you have to try with Bellman formula. So that is a blind rule we are following. Is it clear? Is it clear?
Yes, sir.
Now you see that this particular one is okay, but when you go for that Bellman code, it's almost it is same to that. But here, what additional thing we are doing is edge relaxing we do. See, one more thing, sorry, I forgot to tell you. There is outer loop and inner loop is running. The complexity of this particular Dijkstra's algorithm is n square. So n is nothing but number of vertices, because outer loop is available, inner loop is available. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
Now you go for Bellman fold. See, the Bellman fold is, it is okay. It can handle negative edge weights, unlike the Dijkstra's algorithm, which can handle that non-negative weights. Bellman fold can handle graph with negative weights, but however, graph cannot handle negative cycles. So I will show you what is negative cycle, then you will understand better. So look at here, there is a one simple graph I'm taking. Maybe 0, 1, maybe it's a directed graph, it's a 2, and again 2 to 0 it's there. Maybe you have a cycle there, maybe cycle might be there. So here you are having weights of that. So this is 2, -3, -1. Let it be like this. So in this, what happened, not only the negative weights, negative cycle also involved. What is the negative cycle? First time, when do you say that this is source? It's a single source. Always we choose one source only. We don't change the source. Source is always single. First, we start from 0 to 1. So it contains infinites. Am I right? Am I right or wrong? Infinite, no? Hello?
Yes,
sir.
sir.
So 0 to 2 reachability, this infinite will go, 2 will come. So next time 0 to 1, 1 to 2, the reachability already 2 is there. 2 minus 3, it's going to be -1. Is it right? Is it right?
Yes, sir.
Again 2 to 1, if you run it, already I said source is having a distance of this 0, because initially you are at this. So this -1 and this -1, it will become -2. Is it less than 0?
Yes, sir.
So that it is updated with -2. Again -2 and 2, so it will become 0. 0, is it less than 2?
Yes, sir.
Yes.
So that it is updated with 0. 0 and -3, is it less than -1?
Yes, sir.
So that the values are not stabilized. What happened there? Not stabilized. This stabilizing is not the job of the Bellman code, but it can detect it. It works the negative weights, but it doesn't work with negative cycles. It will report, sorry, this graph is having a negative cycle. Please check. That is informal. But if negative cycle is not there, it works. Even negative edges are there. Maybe you have a graph like this, 0, maybe same graph I'm taking 1, and this is 2. Maybe you are having 2. So this is a source vertex. So you are having, this is 2, and you are having -1. Okay, I'm sorry. This weight, no. This is 2. This is -1. This is 2. Maybe something like this. So here negative edge weight is there, but it doesn't create negative cycle. See this. Initially it is infinite. Am I right? Is it right? We started from a source. Hello, is it right?
Yes, sir.
So
Yes, sir.
here 0 to 2 is updated, 2 to minus 1 is updated, 1 to 2 is updated, 1 to 2 is not updated because 0 is the lowest value, it is not updated. Is it right? We don't have a cycle, no? Negative weight is there, but no cycle, no issue.
Yes, sir.
Values are stabilized. Is it stabilized or not? We don't go back 1 to 1, sorry, 2 to 0, because 2 to 0, if you try to go, it's already 1, 1 plus 2 is 3, 3, is it less than 0?
No.
So that it doesn't go. So that Bellman Ford works with negative weights, but it doesn't work with negative cycle. That's an important thing, because generally in the quiz examination they'll give it what are the below statements are right or wrong in terms of Dijkstra's, in terms of Bellman Ford. Then you need to find out it. So the next one is, it can detect the negative cycles. As I said, it works with negative edge weights, and it will detect that negative cycle. I'll show you how it is detected. Maybe one particular example we'll take it. Of course, same like Dijkstra's algorithm, disconnected graphs also we can handle, like but source has to be changed. If you have two components are there, first source is this, run the Bellman code again you take a different source, again you run the Bellman code. So here one more important thing is, it uses dynamic programming method. So actually a dynamic programming is a new strategy of programming. Maybe 8th or 9th week we have exclusively dynamic programming strategy. But in simple terms, what is the dynamic programming is, it is having an array of distances, gradually they are updated, each particular values, like first value, second value, third value, something like multiple values are created, like previous values are used with current values are updated, the next values keep on using it values. So Bellman code also, it works with director and undirected. Dijkstra's also works with director and undirected. But only thing is, if it is directed graph, we have to double the edges. Sorry, undirected graph means we have to double the edges. But directed graph, you need not double the edges. But rest of the code is same. Is it clear? Shall I go for the conceptual explanation of Bellman code?
Yes, sir.
Fine. So now we are going for the Bellman code. Of course, the same graph I am taking. Interesting thing is, they are using negative weight. Did you see the -4 there? Here -2 is there, -1 is there. Negative weights they have taken. Let you check it. Same graph I am taking. Yes, same graph, just a simple miniature, and we try to run the Bellman code. So just give me 1 second. I'll just get back in 1 minute. Yeah. So please look at here. First, we think about that the Bellman code, it works with a concept of called, just going for the black. Yes. So the Bellman code, it works that it's going that edge relaxation concept. Edge relaxation. So what is the edge relaxation? If n vertices are available, you need to do that n minus 1 edge relaxations. We'll see that what is the edge relaxations. So each particular maximum n minus 1 edge relaxations you do. If you relax all edges, so that all possible paths are covered. So if you have relaxed that all n minus 1 edges, it means that all possible paths are covered.
Uh,
Paths are covered. Hello.
Excuse me, sir.
Yes, yes.
So actually, I lost the connection. I didn't understand the last one you were talking, right? The negative.
Yeah.
What is it?
Which one?
Yeah, about the Bellman before the Bellman algorithm. You talk about the negative weightage, right? So the negative cycling.
Yeah, yeah.
Yeah.
So
So
actually, negative weights is there means Bellman food works, but negative cycles are there means Bellman food doesn't work, but it will report the cycle is there. Cycle means what? Every time when you run it, the values are not stabilized. Is it clear? So please look at here. This is what the samples have taken. This is clear.
mhm.
So this way, if this is a graph, it is having 0, 1, 2. You are having a edge weight of 2, -3, -1. Okay.
Okay.
Now 0 to 1, already infinite is there. So this 2 is less than infinite, 2 is updated. Is it right?
Correct.
2
Yeah.
to 2 to -3, sorry, 2 to sorry, 1 to 2, already 2 is there. 2 minus 3, it will come -1. Is it clear?
Less than negative. Yeah. -3.
Now
Okay.
minus 1 to this, sorry, the 2 to 0, if already 0 is there, no? Clear?
2 to 0.
So
Okay.
2 to 0, if you consider already 2 is available with -1, -1 and -1, it's -2. Clear?
Yes. Yes. Yes.
Is it less than 0? Is it
Yes,
right?
yes.
So
Yes.
that
Yes.
it is updated. So
Yeah. Yeah.
again if you run it -2 and 2, it will become
Ah.
0. So values are not stabilized
Yes. Yes.
because
Correct.
of negative cycles. Negative cycles.
Hmm.
But
Got it.
negative edge weight doesn't create any problem. Clear?
Yeah. Yeah. Clear. Clear.
Yes, fine. So now this graph they have taken is negative weights only. We are sure no negative cycle. How can you check it that no negative cycle is very simple. So please look at here. Even you see that 6 to 1, 1 to 5, 6 to 1, 1 to 5. So already 6 is there, -4, -4 and this 2. And again from the 5, there is no connection to 6. Is it there? No cycle, no?
No, sir.
So no problem. Next one. If you consider this, maybe here it looks like a cycle. 5 to 4, again 4 to 5 is there. So let you see that -2 and this is -1 because we are trying to add all these. -2, -1, it is -1. -1 and 3, it's a 2. It's a +2, no? Is it clear?
Yes, sir.
So +2 and -2, sorry, -1, it's a 1. So it doesn't create negative cycle. Is it right? Is it right? If again you are getting any negative value, so that it is a problem. So negative cycles are there means it doesn't work, but it will detect it. Sorry, there is a negative cycle. Values are not stabilized. You take care of it. I cannot do. But there is no solution. But simply it will inform you. Is it okay?
Yes, sir.
Now, the important thing of the Bellman code is if n vertices are there, n minus 1 edge relaxation has to be done. What is the edge relaxation is all possible paths are covered means one edge is covered, one edge is completed. So all possible paths. So here also maybe you are creating one matrix which is we have already created so far for Diksha's. Similar lines we go. So let me go for uh, the same whatever the graph. How many vertices are there here? How many vertices?
Sir, 8.
So yeah, it is 0. Yeah, it is 8. So let me do that. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, it's done. It's done. 0 to 7. Of course, it is totally 8. So we are trying to go for that. This is the particular matrix title. Of course, it is having all these number of rows and columns. So here, how many number of edges are there? That particular edge relaxation we try to do. So let it be that the edges also I want to write it because edges are more important. So let me consider the first edge is 0 to 1. Is it there? 0 to 1 edge is there, no?
Yes, sir.
So another edge we are taking 0 to 7. Another edge is 1 to 5. Another edge is 2 to 1. So another edge is 2 to 3. So another edge is 3 to 4. Another edge is 4 to 5. So another edge is 5 to 2. So next one is that 6 to 1. The next one is that 6 to 5. I think it's the last one. 7 to 6. Is it right? These edges are there, no? These edges are there.
Yes, sir.
So now this is all the particular edges, sorry, vertices. We are having one particular matrix. Of course, we are taking it as edge relaxation job. So we try to fill all of them. Maybe how many it is possible. At most, we try to fill all of them. Of course, maybe one more row is required. We don't worry about it. So anyway, that's okay. So this is my particular matrix, this dynamic array or matrix we have for the edge relaxation we try to do. So this is my edge relaxation matrix. Yes. So let me start that. So here also the source we are fixing because it's also single source shortest path. So the source is that my 0th vertex, its distance is 0. The rest of them we are having that infinite. Same initially what we set it for Dijkstra's algorithm. Same thing in the Bellman code also. This is infinite. This is infinite. All this is okay. That's all. Initially, we'll fix all of them. These are infinite. All of them. Of course, 0th one is it's 0 because we start from the vertex 0. We fix it. Now let's be started. We are trying to run it. Now from the 0th vertex, we are trying to update. Let me update the values. We are taking a red color. From the 0, we are trying to, each vertex we are trying to 0 to 1. What is the 0 to 1? Already 0 to 1. Infinite is there, no? Is it there?
Yes, sir.
So of course, these things we can make it zeros. No issues about it. No updating further required. Yes. So 0 to 1, already infinite is there. This 0 plus 10, 10, it is updated with 10. Okay. Is it right?
Yes, sir.
Next. So this edge is relaxed. Next one. So we are going with 0 to 7. So already infinite is there. This 8 is going to be added. So infinite less than get value. So that 8 is updated. So that this particular 0 to 1 is updated. This edge is relaxed. So then after it, next edge 1 to 5. So 1 to 5 is there, no? 1 to 5. So what is a 1 to 5? Already 10 is there. Already 10 is there. 10 plus 2.
12.
10 plus 2.
12.
12. Is it less than infinite?
Yes.
12 is updated. So 1 to 5 is done. Next 2 to 1. Already infinite is there. Infinite plus 1. Infinite plus 1.
Infinity.
Infinite. So that it is not updated. 10 is as it is only. Is it right?
Yes,
Is
sir.
it? So this edge is also over. Now 2 to 3. So what is my 2 to 3? Infinite and this 2 to 3. Infinite plus 1. So that infinite. So that same value it's there. It's done. Next one. Next edge is 3 to 4. So this is infinite and infinite. Same thing here. Next one is 4 to 5. So infinite minus 1, it is infinite. So that it is also same. No, it is 4 to 5. Next one, 5 to 2. Any updates are there? 5 to 2. So where is my 5 to 2? Yeah, it's a 12 and this one. Please remember 12 and this minus 2. What is this value? 12
10.
is 10. So that it is updated with 10. So 5 to 2 is updated. Next 6 to 1. So where is my 6? Yes. 6 to 1. Already infinite is there. Infinite minus 4. So no chance. Infinite is as it is. 6 to 1 is over. Next one is 6 to 5. So my 6 is having 5 infinite. Infinite and this minus 1. No chance. So infinite is as it is. 7 to 6. So my 7 to 6, already 8 is there. 8 plus 1 is 9. 9, is
9.
it less than infinite? Yes. So 9 is updated. So one phase of age relaxation is over. Let me update our values. So what is my 0 to 1 is 8. 0 to, sorry, I'm sorry. 0 to 1 is 10. Next one is 0 to 2 is there. 0 to 2. So it is 12. This is 10. This is 12. Next one, 0 to 3. So what is my 0 to 3? So this, or that infinite as it is. Is it as it is? No. 0 to 3. Hello.
Yes.
Next one is 0 to 4. So where is my 4? Here. So we have that 0 to 4. It is infinite. Where is my 5? It is 12. Where is my 6? It is 9. Where is my 7? It's 8. This is one phase of age relaxation is done. This way, you need to check that another phase. So another time we are running, so that we are trying to change the color is one more. So now again we try to do it. Again we try to do that. Again we try to do means again 0 to 1 we are checking. So what is my 0 to 1? It is as it is, no? Is there any change? Is there any change? 0 to 1?
No, sir.
No change. So as it is, it's there. Next one, 0 to 7. So is there any change?
No, sir.
No change.
No.
1 to 5. So 1 to 5. So where is my 1? This is my 5. So here the 12 is there as it is. Is it right? As
Yes,
it is,
sir.
no?
Yes,
Next
sir.
one.
Yes.
2,
Yes,
yeah,
sir.
2 to 1. We are going with 2 to 1. So this is 11. 2 to 1. Already 10 is there. This is 1, 11. 11 is updated. No chance. 10 is as it is. Is it clear? Is it clear?
Yes, sir.
Now,
Yes, sir.
2 to 3. So we are going with 2 to 3. This 11 we are getting. 11 is less than infinite. So is it updated? Yes. So that 2 to 3 is updated. Is it clear?
Yes, sir.
Next one. 3 to 4. We have a 3 and 4. So already 11 is there. It's a 3. So it contains 14. So 14 is updated. So 3 to 4 is done. Next one, 4 to 5. Yes. So 4 to 5 is here. Where is, yeah, 4 to 5. Already 14 is there. 14 minus 1, it's a 13. 13, is it less than 12? No. Is it less than 12? No. Is it right? No. Hello. Hello.
Yes,
Yes.
sir.
So that 4 to 5 as it is 12. No change in that. Next one, 5 to 2. So here 5 to 2. So this 5 is already having 12. 12. Oh, sorry. I'm sorry. Yeah, here it is. Sorry. 5. 12 is there. So 12 minus 2, it's a 10. 10 is already good value. So we don't change it. Here, interesting thing happens. Please see that. 6 to 1 is there. What is my 6 value?
9.
9.
Minus 4.
5.
Yes. 5 is better value than this 10.
Yes.
So that
Yes, sir.
it is updated. So that 6 to 1 also it is updated. And now two more edges are the 6 to 5. So the 6 to 5, it's already 9. So here it is minus 1. Here also interesting thing happens. Through that is minus 1, it's 8. It's a better value than 12. 6 to 5. So this is done. Now 7 to 6. Yes. 7 to 6 is that 8 plus 1, 9. 9 is same value. It's a better value. So we don't update it. So now we have the updated values of this. What are the updated values of this? So 0 is 0. Whenever it comes to 1, earlier it is 10. Now the recent updated is 5. So 2, it is a 10. So earlier it is, I think, yeah. Oh, something is wrong. Here it is infinite. Maybe, I don't know. Maybe we did someone. But here it is 10 is the right value. Maybe I think so. I'm sure. So let it be then. Maybe how this 12 came earlier. Earlier 0 to 1, 1 to 2.
10 plus 12.
No. Earlier, how we got this 12? That's what my question.
1 to 5, 1 is 10. So
Uh,
10 to
uh,
1 to 2, 1 to 5 will give
okay.
us,
Okay.
because
It's
1
it's it's 12. 12 and okay, I got it. Okay, 10. It's a 10. So now 3, how much the 3 is? 11. How much the 4 is? 14. How much the 5 is there? It's 8. How much this 9 is there? It is,
9.
sorry, 6. It's a 9 value as it is. And the 7, it is same value, it is 8. So this is edge relaxation. One more edges. Still, these number of times we do the edge relaxation, somewhere values are stabilized. Please focus. Don't worry that we are spending much time, but pretty sure sometime the edge relaxation is final because somewhere the values are stabilized. Now we run it one more time. This is with blue color I'm trying now. So let me do that again. So we try to do again 0 to 1. Any change in the 0 to 1? So
No.
no, because 5 is a better value. The 5 is as it is. Next one is 0 to 7. So we are having 0 to 7. 8 is a better value. No change in that. 1 to 5. Is there any change of it? So already 5 is there. 5 plus 2, it's a 7. 7 is a better value than 8. Am I right?
Yes, sir.
So that 7 we are putting it. So
7.
1 to 5 is done. 2 to 1. So this 2 to 1, 2 is already having 10 and this is 11, so that we don't have chances of any update because 5 is a better value. 2 to 3 we'll try. 10 and 1, it's 11, so no change in that. It's edge relaxation is done. Now 3 to 4 we tried. So already 11 is there. 11 and 3, 14. 14 is a better value already there. 4 to 5. So 4 to 5, it is minus 1. 13. Already 7 value is there. 7 is a better value. We don't want to change it. 5 to 2. So let it be that 5 to 2. So already 7 is there. 7 minus 2. What is the 7 minus 2 value?
5.
So here there is update. So this is 5 to 2 is done. Next 6 to 1. Let me see that 6 to 1. Already 9 is there. 9 minus 4, it's a 5 is already better value. No worries. Now 6 to 5. Already 9. 9 minus 1 is 8. So that 7 is a better value. We don't want to update it. 7 to 6. So 8 plus 1, 9. So that already 9 values existed. We don't change it. So now let it be the same values. We try to do that. So the edge 0 to 1 is 5. And 2 is, where is my 2? Yeah, 2 is, yeah, it is the latest value is updated, which is better than the 10. 3 is 11. And 4 is 14 as it is, and 5 is updated. Earlier it was 8, now it is 7. And the next one is 6. 6, there is no change. 7, there is no change. It's all done. So now one more time. So don't worry, some values are somewhere it is stabilized. So we are going that one more time. Maybe we are using a different color, something like this. So now again one more time. So now again 0 to 1, of course there is no update. 0 to 1 is as it is because there is no other diversion of it. So that same as it is. 0 to 7, it's the same, no issue. So this is also done. Next one is 1 to 5. So any update in 1 to 5, 5 and this 2, it's a 7. So 7 is already existed. So no chance required. 2 to 1, so already 5 is there. Sorry, 2 to 1. already 5 is there, 5 plus 1 is 6. So there is no chance of update. 5 is already better value. 2 to 3. So here interesting thing happens. So 2 to 3 is there. So what is my 5? And this one is 6. So 5 plus 1 is 6. It's a better value than 11. Am I right?
Yes.
So that it is 6. So the 2 to 3 is updated. That is 6. Next one is 3 to 4. So we are having 3 to 4. So this 6 plus 3, 9. So it is a better value than 14. So 3 to 4 is done. Next 4 to 5. So 9 minus 1. So it is 8. So there is no chance of that. So 7 is a better value, 4 to 5. Next one is 5 to 2. So we have a 5 to 2 already. 7 minus 2, it's a 5 is already existed, no update. 6 to 1. So 5 is already existed, no value of changing of values. 6 to 5. So 9 minus 1 is 8. So no chance of update, same as it is. 7 to 6. So it's a 9 only already existed. So this is okay. Now let it be that my values are, this is 0. For the 1 it is 5. And for the 2 it is 5. And for the 3 it is updated to 6. And for the 4 it is updated to 9. Interesting thing. And for the 5, so it is I think it is 7, as it is better value is there already existed. 6 is 9 and 7 is 8. Mostly at this time the values are stabilized. Let me try one more time. So what is there? So we are trying one more time. Maybe you are taking here a different color. Yes, we take this color now. So one more time, if you run it somewhere, you will get it. Definitely values are stabilized. Now we run it 0 to 1, no update as it is. 0 to 7, no update. This next one is 1 to 5, 1 to 5, 5 and this 7. Okay, no update, no issues. Next one is 2 to 1. So already 5, 6 is already updated, no problem. 2 to 3, 6 is already existed, no chance of update. 3 to 4, already 6 and this 3, 9. So that no chance. 9 is a already existing value. 4 to 5. So 9 minus 1, it's a 8. No chance of update. 4 to 5 is already there. 5 to 2, it is uh, 5 to 2 is this already 7. 7 minus 2, 5 is already existed. It's already existing value is better value. 6 to 1. So where is my 6? 6 to 1 already this minus 4 already 5 is existed, no issue, no problem. 6 to 5, it is 9 minus 1, 8. 7 is already better value, we don't want to update it. So 7 to 6, it's already 8. It is 9 is 9. By this time values are stabilized. Even you run it 2 more times also, maybe this is n minus 1 times you run it also, these values are stabilized because it is having negative edges but no negative signs. Hope you understand. Is it clear? Is it clear?
Yes, sir.
Now,
So what?
hmm,
So you can you repeat the last sentence?
stabilized. Even you run 2 more times because already 8 vertices are there. No, we are running 7 times. Is it right? Is it right?
Yes, sir.
So even after maybe first 1, 2, 3, 4, by the 4th time values are stabilized. Is it right?
Yes, sir.
Even you run one more time because 5th time also we checked it with orange color. By the 4th time itself values are stabilized. Even you run 5th, 6th, 7th also values are same will be repeated. Is it right?
Yes,
Once
sir.
it is stabilized, it is stabilized. So it can work. Negative edge weights also it works. But there is an issue with negative cycles. Let me see how the values are not stabilized. We check with other graph. Is it okay?
Sir,
Hmm.
how did you decided that you have to
No. Wait. We have to run it n minus 1 iterations without stopping. No doubt. Clear? Clear?
Okay, sir.
But how would you know that values are stabilized or not? As after running n minus 1 iterations, you get a result. Is it right? Is it right?
Yes.
So we run one more time, we get another result, some x. One more time, intentionally. Is it clear? Is it clear?
So we'll get the same
No,
result.
Yes,
no.
sir.
One more time, one more time. Already n minus 1 times you got it. You got a one result. This is one result. Maybe the final row is one result. Is it right? Clear?
Okay, sir.
Intentionally, after iteration, we'll run one more time a result x. One more time. That is a new value of result x. Let me compare these two. Is it same values are there? Means it is not having negative cycles. Hope you understand. Clear?
Yes, sir.
So that's what we'll try with a graph with negative cycles. See this? This graph contains a negative cycle. Maybe by oversight, even you look at where is negative cycle. I don't find it. But let me run the Bellman code here. Can we run this one, Bellman code?
Yes, sir.
Because it's a simple 4 vertices one. See what we do is same thing here. Maybe 0, 1, 2, 3. So you are having this initially. Yeah, maybe yeah, it's okay. So we are having this n minus 1 edge relaxations has to be done. You are having this. So initially this is, and we are having infinite. We are fixing this. So this is, maybe I'll use it initially black only. This is 0 because it's a source. This is infinite. This is infinite. This is infinite. So let me do that. So we are having this. So always this is 0. No issue now, because maybe initially we may think about it 0. Later we think what happens then. So let me run the Bellman code now. So when do you do that? 0 to 1. So this 0 plus 1, it's a better value. So that, so I'm doing with a red color. Maybe it's a first edge relaxation, second edge relaxation, third edge relaxation. So let me do that. So 0 to 1, already 0 plus 1. So infinite will go, 1 will come. Am I right or wrong?
Yes, sir.
So
Yes, sir.
next one. So maybe we'll write it. The edges are 0 to 1 is the first edge, and second edge is 0 to 3, and next edge is 1 to 2 as per the graph. Next one is 2 to 0. Next edge is 2 to 3. Yeah, this is our edges. So now let you see that. So 0 to 1 we have done it. This is done. Next 0 to 3. So 0 to 3. So already its infinite is there. You are updating with weight 1. So 0 to 3 is done. So next one 1 to 2. So already 1 is reached with 1. Minus 4. So minus 4, is it less than infinite?
Yes.
So that it is updated with minus
Minus.
3. Minus 3. Is it right? So 1 to 2 also done. 2 to 0. So already 2 is there. Minus 3 is there. We are having this one minus 1. Minus 1, is it less than value of 0? Is it right? Hello?
Yes, sir.
So that it will become
Yes, sir.
minus 1. Am I right? So 2 to 0 also done. 2 to 3 we'll try. So already minus 3 is there. Minus 3 and 3, it will become 0, because 0 is a smaller value. So this is also done. Now the edge relaxation is done the first cycle. We got the values is 0 is minus 1. So 1 is getting it is 1. 2 is getting the value of minus 3. 3 is getting the value of 0. 1 edge relaxation is over. Now we'll try one more time. So one more time we'll try it means minus 1 and 1. What happens? So I'm going with a different color. Minus 1 and 1, it's 0. So 0 is a smaller value. So 0 and 3, 0 and 3, minus 1 and 1, it's a 0. So no update, as it is, it is. This is over, this is over. 0 to 3 same value, no? Is it right? Next one, 1 to 2 we are trying. So 1 to 2, already 0 is there. 0 and minus 4, it's a minus 4. Minus 4 is a smaller value than minus 3. So it is updated with minus 4. Am I right?
Yes.
Am I right?
Yes.
Next, 2 to 0. So 2 to 0, already minus 4, it's a 2. And minus 2, minus 2 is a better value than minus 1. So minus 2 is updated. Next, 2 to 3. So already 3 is there. So minus 4. So we are getting minus 1. We are getting minus 1. This is also done. The latest updated values, this is minus 2. And this 1 is having this 0. And 2 is having this value of minus 4. And 3 is having value of minus 1. Still, even you run it, maybe, n minus 1 cycles you run it. So you get some values, you put it a result, and you stop the iteration. Out of it, you run one more time you do the edge relaxation. So then you get some result X. Of course, result we are using and we are generating result X. These two we are comparing. If you compare these two, if these two values are not same, you say that, sorry, this graph is having negative cycles. This can be detected by Bellman code. It works with negative edges, no problem. If negative cycles are there, the values are not stabilized. If the values are not stabilized after n minus 1 edge relaxations, so you should immediately run one more time and you should compare whether it is having a negative cycle or not. So that Belmont Ford is having a facility, whether you want it or use it or not is your choice, but it is having a facility. So let me explore the code. So I'm going for the code. It is almost, the logic is same, but some more additional loop is used. See, I'm not using adjacency matrix because adjacency list is somewhat optimized. Yeah, this is adjacency list. We are taking infinite same way, because earlier I said what is the maximum value of the graph they are taking. Distance matrix they are taking. Of course, they are not taking visited matrix. Don't worry, because visited matrix they are not printing. Then why to use it? They are not using. No issue. So now, initially all of them they are putting it infinite, except the starting vertex. Already starting or source vertex they have chosen is 0. You can choose something else. Whatever you want to choose is your choice. Now you see that interesting thing here. There is an outer loop. This is exclusively for using the edge relaxation. How many number of vertices are there? That number of times you are running, that is called n minus 1, because we are using the keys. That is called edge relaxation. Inside, we are taking each particular vertex and the distance from u to v is taken. Out of that, already existing distance plus added distance, if it is smaller than available distance at destination, same formula, whatever I said earlier formula is same thing here it is done. But here one thing is, there is additional outer loop they are using, because every time you need to rerun that again, that all edges, all calculations. But if you see that Dijkstra's algorithm, only 2 loops are available. But in the case of that Bellman code, we are running one more outer loop. So then what is the complexity of this?
N cube.
Yes, it is n cube. Please see that it's n cube. So of course it is v cube or n cube is both of them as, sorry. If it is actually where it is, E is nothing but, sorry, it is adjacency matrix, and yeah, here it is n cube. But whenever adjacency list they are taking the complexity, you look at here. Here it is the range of rows they are using, range of columns they are using. Definitely rows and columns are same now here. Am I right? Am I right or wrong? Because If it is n number of vertices are there, we are trying to run that n minus 1 edge relaxations. It is almost equal to that. These two are equal to the n square. Is it right? Is it right?
Yes, sir.
Outermost one is for edge relaxation, so that is one more n is added, so it is n cube. If it is adjacency matrix, if it is adjacency list, somewhat complexity is reduced to v into n. V is nothing but number of vertices, e is nothing but number of edges, because so you could see that the outer one is that number of vertices, because keys they are taking the keys. But when you come to inner one, they are taking edges. Every u they are picking up, that u they are trying to find out it. The destination u they are trying to find out it. That u adjacent only we are taking. We don't take every adjacent. Whatever u you are picking of it, that u adjacent only we are picking of. That u adjacent means that edges only. We don't touch other edges. So in this case, adjacency list using is better than that adjacency matrix. But one thing you need to do it is, once you got the distance final version, maybe you want to check that whether my the edge stabilization is done, values are stabilized or not. I want to check it. What should I do is, I will take this distance and one more time we run this loop. One more time, maybe we try to run one more time this loop, maybe this outer loop and inner loop, one more time, just one more time, just we are repeating it one more time. We get it a distance x value, whether this distance and that distance is same or not, we'll check it. If they are not same, we say simply here it contains that edge cycle is having negative cycles, so Bellman code can detect that negative cycles. This is what you can say, every time we try to detect that whether the values are stabilized or not, so until all the particular edge versions are finished, we don't come to conclusion. This is what it works with the negative weights, but it doesn't work with negative cycles. So hope you understand. So don't think it is a complex one, but please refer that the recorded video. Even I try to put it in the white YouTube streaming in the tomorrow. Still, just you recap that how the edge relaxation is going on. So then you try to see that what is the code, how it is working. So hope it's okay. Shall we go for the next one?
Sir,
Tell me, Bhavya.
sir, what is edge relaxation you said? Like,
So what one version, second version, third version? See, this is first version, second version. These things, how many times you need to do? There is a limitation, no? Where should I conclude my iterations? So that concluding means that all the edges, every time you need to check it up to n minus 1 number of times. First time, second time, third time. See the colors I am using, no?
yes,
First
sir.
time we have that. So that is called edge relaxation.
So we are iterating that.
Yes, outermost loop is there. That is called edge relaxation outer loop.
Okay, sir.
So
Sir, I
if-
thought it would be something about time complexity.
no, time complex. See, one more thing. Again, I'm referring you. Time complexity is not a matter in the graph algorithms.
Yes, sir. You told it. Yes, sir.
So even they are asking in the OPP examination, they try to make you to solve. They don't check the huge data time complexity. Only they'll check for the log n sorting algorithms. They are very strict about it for time complexity. Okay. Yeah.
Got it, sir.
Yeah. Fine. So these two are single source. Whatever you have seen that Dijkstra's and Bellman code is single source. Let's we see that multi-source shortest path. So here, I'm talking about it, but algorithm processor is somewhat very easy, but only thing is different versions of matrix are there. See, look at Floyd version. There are two mathematicians actually. Up to Dijkstra's and Bellman code is one mathematician name only. They're putting their name. But Floyd Warshall is a combination of two mathematicians. There is a Warshall is a different mathematician. Floyd is a different mathematician. So they have developed this algorithm. It's an all pair shortest path. Why do you say the all pair is? Just quickly, I want to tell you. See, always if it is single source, 0th vertex to first vertex, 0th vertex to second vertex, 0th vertex to third vertex we'll try. That is Dijkstra's and Bellman-Ford. Am I right or wrong?
Yes,
Bellman-Ford.
sir.
But whenever Floyd-Warshall, what it will do is, first it will try 0 to 1, 1, 0 to 2, 0 to 3. Next it will try 1 to 2, 1 to 0, 1 to 3. Next it will try 2 to 0, 2 to 1, 2 to 3. Then it will try 3 to 0, 3 to 1, 3 to 2. All pairs you will get it. Every pair, 1 to all pairs, 2 to all pairs, 3 to all pairs, it will try to investigate all the possible paths. All the possible. So what happens, we get single row result in the case of Dijkstra's and Bellman-Ford. But in the case of this Floyd-Warshall, you get multiple results. The result is going to be that rows and columns. So if you could see that the result of this, let me stop this. Yes. Yeah. See, the results of this one is simple. It's a single kind of dictionary. Is it right? Is it right? It's a single
Yes.
source, no? So, but
Yes.
whenever you go to the output of these, the interesting output is like this. So this what it indicates is from 0 to all other vertices, what is the path? From 1 to all of them, from 2 to all of them, 3 to all of them, 4 to all of them, 5 to all of them, 6 to all of them. So this is, we are getting the output is combination of rows and columns, because every vertex to other vertex, what is the shortest distance? So that we are trying to find out it. But one interesting, simple and easiest formula to remember is very simple. Every time we are trying to find out each vertex to other vertex, direct edge and indirect edge. So I can tell you a simple kind of thing. What I want to tell you is, for example, we are having 0, maybe something like this, and we are having this 1, we are having this 2, this path is there, maybe you are having this, and there is a direct edge also maybe there, maybe this we can say that. What I want to tell you is, I want to check the reachability from I to J. I want to check the reachability from I to J. So maybe I've taken it's a direct graph. So the path is like this. 0 to 1 is there, 1 to 2 is there. Is it clear? These directions are clear?
Yes, sir.
Now, what I want to check is, this I and J is there. There is one more edge is there, which is called K. Maybe via K we are checking about. What I want to do is, whether I will check that the minimum, is it minimum, I to J is minimum, or is it direct path is minimum, or we are trying to do that I to K and
K to J.
yes, K to J. These two plus. So I to K, K to J. So these two plus. Out of this, which is a minimum we are getting? We choose that way, no? Is it right? Either this path is minimum, or we come here and then we come here. This is minimum. So hope you understand what is this one. Is it clear? Directly we want to reach it from I to J is minimum, or reaching via K is minimum or not, we are checking. That is what particularly we are checking. So that what happens, here different versions of shortest paths happen. What you call is, different versions of shortest paths. Different versions of shortest paths. SP means shortest paths happen. We'll see what is this shortest path matrix, how it looks like. So hope you understand this concept. Direct edge is minimum or via K is minimum. That's what we are trying to check. Is it clear then? Is it clear? Hello?
Yes, sir.
The minimum function we are applying, either direct edge is minimum or via K is minimum or not, we are checking. So just give me 1 second before I'll start the algorithm process. Just give me 1 second. Yeah, just one. So here, please understand, there is a different versions of shortest paths. We'll see what are the different versions. The first version, second version, these versions are there. So what exactly it is, already I said, we are trying to find out the shortest path from 0 to others, 1 to others, 2 to others. So what exactly, every time Dijkstra's algorithm, if you change the source vertex, if you run it, that is called as that Floyd wash. Is it right? Is it right? If you run Dijkstra's algorithm multiple times by changing the source vertex, it's going to be Floyd wash. Is it right or wrong?
Yes, sir.
So here the strategy is same, but they are trying to use a big, two-dimensional matrix they are using. So let you take the same graph, maybe whatever the graph it's there. What we are trying to do is, first we are trying to, making a matrix. Let it be the matrix is, so all these one, we are making it as 0, 1, 2, 3. This combination of rows and columns we are taking, maybe something like this. I'm using that each particular matrix is different color. This and this. This is 0, 1, 2, 3. So we are taking it the 0, and this is 1, this is 2, and last one is 3. So here the first row represents that 0th row represents that 0 to other vertices. What is the shortest path? This 1 is representing, because already I said it is 1 to others, 2 to others. So the second row represents that 2 to other vertices, what is the shortest distance? 3 to other vertices, what is the shortest distance? So this is what I want to do it. Now, hello, is it okay?
Yes, sir.
Yeah. Mm.
Isn't like they must be connected, right, sir? Like 0 is connected to 1, 2, 3, but 2 isn't needed necessarily to connect it to
Maybe connected or not is not a issue. If it is not connected, what is the value?
0.
No. For example, I have a graph like this: 2, 3, okay, 1. This I started. The source is 3. Clear? Fine.
Yes,
So then, if the source is this 3, what is the final result of any shortest path algorithm? If there is no reachability, they still remain infinite. Am I right? Is it right or wrong?
Right, sir.
If the result it contains that any vertex is infinite, what does it mean is it is not reachable. Maybe it is not having a direction, or it is not having edge, or it is a disconnected vertex, maybe something like that. Is it clear?
yes, sir.
So that if you start that particular traversing from 3 to 2 is possible, 2 to 1 is possible, 1 to 0 is possible, no issue. Clear? Is it clear?
Yes, sir.
For example, if you start from 1, 1 to 0 is possible, 1 to 3 is possible. After reaching 3, I can reach 2. Is it okay? Now we get other than infinite value. Clear? Is it clear?
Yes.
But if you do this one is a particular one as a Floyd Warshall, the first reachability for the one is 1 to 2 is reachable, 2 to 3 is reachable. Am I right?
Yes, sir.
So I'm sorry, 2 to 1 is reachable, 2 to 1 is reachable, 1 to 3 is reachable. Okay, next one.
Yes, sir.
Next one is 2 to 3 is reachable, 2 to 3 is reachable, and 2 to 1 also reachable. Clear? Maybe directly or indirectly, it doesn't matter. Fine, fine.
Yeah.
Yes, sir.
But whenever you start from 3, there is no reachability. So from the 3, the reachability for the 2 is, 1 is infinite. The reachability for the 2 is infinite because we cannot reach it. Fine, fine.
Yes, sir.
So that happens, that generally happens even you change the values and try to work it out. Algorithm, you get the outputs are infinite. So infinite you are getting means that is not having any direct or indirect edge. Simply, it is not reachable. Is it clear? Fine.
Yes, sir.
Now this is, I'm starting the Floyd-Warshall. In the Floyd-Warshall, it is the first version of matrix. What is the first version of matrix is very simple. We are taking uh, SP0, maybe shortest path 0. So the shortest path 0 means we are trying to find out 0 to other vertices. What is the possible, uh, you know, uh, all the possible things, all the possibilities. So let it be then. We are trying to do that. 0 to 1. So 0 to 1 is the, sorry. First I have to fill it. 0 to 0 is reachable is 0. 1 to 1 reachability is 0. 2 to is 0. 3 to is 0 because always diagonal values are 0 because it's not having self cycle edges. Is it having self cycle? No, it's not having. Is it right? Is it right?
Yeah.
Now, so now you try to fill it. 0 to 1, is it reachable? Yes. 0 to 1, how much is that? 3.
3.
Next one. So 0 to 2, is it reachable? 0 to 2? Direct edge. I'm talking about direct edge, please remember. It's
No,
a
sir.
direct. So because it's SP0, so 0 to 2 not reachable, it's a infinite. Next one. 0 to 3, is it reachable? Yes. Fine.
Yes.
Next one. So the next one is, we are trying to go with it. 1 to 0, is it there?
2.
1 to 0? Yes, 2. Next one. So 1 to 1, okay, it's a 1 to 1 self edge is not there. So 1 to 2, 1 to 2, no
No,
possibility
sir.
because 2 to 1 is there, 1 to 2 is not there. So it is okay. So 1 to 3, yes, it's there. 4,
4.
it's done. So the next one is that 2 to 0, no there. It's direct edge is not there. So infinite. 2 to 1, yes, 1 is there.
1.
Next one is 2 to 2, anyway, it's not there. Self edge 2 to 3, no way. So it's
No.
infinite. Direct edge only I'm talking about. One more time. Next one is 3 to 0, no way. So it's
No, sir.
infinite. Next one is 3 to 1, no way. 3 to 2, yes, there is edges there too. 3 to 3 is not there. This is SP0 we are available. What is this one is called SP0? The shortest path 0. 0 to other vertices we know. So how would you know that 0 to other vertices is? So this 0 to other, this one. So I'm changing a color. Yes, I'm taking a color. Yeah, it's a black color. So this completely it's 0, 1. These values are belongs to 0. So 0 to others, others to 0. Am I right or wrong?
Yeah.
0th
Sir.
row, 0th column. So 0 to others, others to 0. So is it clear?
Yes, sir.
We got it.
Yes.
So now using this, we try to investigate the first one. So let it be that SP1. I'm changing with a color called SP1. So whenever another version of SP1 we are building, what does it mean? Via 1, vertex 1. So this vertex 1 we are trying to trace out it. Now what I'll do is The same matrix it is. Interesting thing I'll do. What is the interesting thing I'll do is, so here 0, 1, 2, 3, 2, 3 and 4, 0, 1, 2 and 3. We are taking this. Yes, we are taking this. Now what I'll do is, these diagonal values are as it is. Via 1, when I'm taking, I try to get these first row and first column values are as it is we are bringing. First row, first column values as it is. Remaining values only we are calculating. First row, first column. This one. So I'm getting these values are like this. This one and this one. These two values I'm getting as it is. And I want to put it in the version. So these first row and first column. First row, first column means this 2, this 0, this 2, 0, infinite. Infinite. And next one is 4. Similar with these values also. These values. So I'm getting 3, 1, and infinite. Remaining all we are calculating. So while you are calculating remaining values, interesting thing happens. So please see that what we are trying to do is, we are trying to do that 0 to other vertex and via A also, via 1 also we are calculating. From 0 to other and via 1 also we are calculating. See, I am talking about 0 to 2. What is my 0 to 2? Wait, please check the graph. 0 to 2.
So
0
we
to
don't have infinity.
Yeah, that's what. Please let me know what is that. It's infinite, no?
Yes, sir.
So via 1 we are going. Via 1 we are going means 0 to 1 plus 1 to 2. Is it right? Because
Yes,
already
sir.
we know this one. I to j direct one. I to k plus k to j. So what is this k is? Via 1 is the k. Is it right?
But we don't have
Wait. So what is my 0 to 1? What is my
3.
0 to
3.
1? 0 to 1 is 3 plus 1 to 2.
We don't have infinity.
So that infinite plus infinite, is this one is less than this one? No, not happen. So both are equal. So we are having the same thing, so that the value of this infinite is as it is. So what value is remaining? It's infinite. 0 to 2 is infinite only. Same, we maintain same, no change. Is it okay? Now 0 to 3 we are trying. 0 to 3
5.
via 1 also we'll try. So 0 to 3 means 0 to 1 we can try, plus 1 to 3 we'll try. Is it right? Is it right? Hello?
Yes, sir.
So now 0 to 3 we'll see. What is my 0 to 3?
5.
Yes, very good. 5. Next one. So 0 to 1,
3.
3. Plus 1 to 3,
4.
4.
4. So does 5 is less than or 7 is less than? What is less than? Which is the minimum? 5 is
5.
minimum, no? So we are keeping this 5 is as it is. No issue. Next. So this one you need not touch it, because it's already, this is already filled from the previous thing. No issue, because via 1 means previous matrix values we are getting all first row and first column is okay. Next we are going this place. So when you are going for this place, 2 to 0 we are trying. So what is the different ways 2 to 0? It is 2 to 1 plus 1 to 0. Is it right? Because 1 is via through 1. Is it right?
Yes, sir.
So 2 to 0, what is the value? It's there already. 2 to
Infinite.
0. 2 to 0.
No, infinity, sir.
Infinite. So that no directed, it's a infinite. So next one. 2 to 1, it's 1. Is it right?
Yes, sir.
So 1 to 0?
2.
Yes. So this 3 is there. This is greater than this. So what is updated this one now?
3.
Yes, 2 to 0 is updated now with 3. So earlier we are getting 2 to 0 is 3. Now it is 3. How did you get this 3? No, if you want to go for 2 to 0, via 3 if you go, via 1 if you go, you are getting that value of this. So this is 1, this is 2. So that's what we got, the value is 3. So now the infinite is gone. So anyway, this is already okay because already filled, because already we got it from previous. This is 2 to 2 is not there. And one more time we are checking is 2 to 3. Next one is 2 to 3. So 2 to 3, when you are checking, there are two ways. 2 to 1 we can check it, plus 1 to 3 we are checking, because via 1 it is. So 2 to 3, how much is there? 2 to 3? Infinite, no? Direct
Infinite.
edge is not there. Infinite. And then 2 to 1 and 1 to 3. So 2 to 1 is 1, 1 to 3 is
4.
So which is less than? 5 is less than. So this is infinite is greater than. So we are updating, this is 5. So earlier it is infinite. Now we got the recent value is 5. So this is done. And the next one we are coming to the 3. So now we are going that 3 to 0. Still we are in the same matrix. 3 to 0. It's a direct one. And we are checking a comparison. That is 3 to 1 plus 1 to 0. So what is my 3 to 1?
Infinite.
So infinite. Sorry, 3 to 0. I'm sorry. 3 to 0. It's infinite. What is my 3 to 1? It is infinite.
Infinite.
Plus 1 to 0, it is 4. So that both are equal. Infinite as it is, we are leaving. No issue there. This all value got it. And this value we have to get it. 3 to 2. The last comparison. 3 to 2. We have two ways. 3 to 1 plus 1 to 2. That's what ij, and then ik and kj. So 3 to 2 is already, it's their value is 2. So 3 to 1 is infinite, plus 1 to 2 also infinite. Is it right?
Yes, sir.
So that this is the better value. So this is via SP1 we got it. Whenever you are creating another matrix, that we are creating is via 2. Then what should I do is, I should copy the second row and second column. I'm copying that second row and second column. That means this one and this one. As it is, we are copying. And diagonal values we are getting. So that another matrix we are creating, which you are getting is a diagonal values are zeros. The diagonal values. This is that via 2. So this 0, 1, 2, 3, 0, 1, 2, 3. Diagonal values are zeros. And the second row and these things we are copying. Let me copy this one. 3, 1, 0 and 5 is as it is. And then infinite, infinite, 0 and 2. Infinite, infinite, 0 and 2. These are copied. Rest of the things only we need to do that calculation. So here also same, we are going at this. First one is again that 0 to 1 we are trying. And whenever 0 to 1 we are trying means there are two ways. 0 to 2 and then 2 to 1. Am I right? So 0 to 1 is 3 and 0 to 2 is infinite and 2 to 1 is, 2 to 1 is, it is 1. Is it right? So
Yes.
this is a lesser value. So lesser value means we can have that 0 to 1. We are getting via this one. If you are going is 3 is a better value. So that we are leaving it is 3 is a better value. So similar way we are going that 0 to 3. So let me try with 0 to 3. 0 to 3 is a direct edge. And whenever you want to try the 0 to 3, via 2 we are trying 0 to 2 plus 2 to 3. So what is my 0 to 3? 5. Is it right?
Yes, sir.
Check your graph. And then, so 0 to 2 is infinite plus 4. So 5 is a better value, we keep it as this. And similar way, we are going that 1 to 0. Again, 1 to 0 possibility we are trying is 1 to 2 plus 2 to 0. So 1 to 2, sorry, 1 to 0 is 2, and this is infinite, and this is 1. So this is a better value, 2 is as it is. Next one we are trying is 1 to 3. So whenever we try 1 to 3, so we try the 1 to 3, there are two ways. 1 to 3 means 1 to 2, and then 2 to 3. So 1 to 3 is 4, and 1 to 2 is infinite, and this is 5. I think 2 to 3 is 5 only, yes. So the 4 is a better value, so that we are updating this 4. And the next one is that 3 to 0. Yeah, 3 to 0. We have two ways then. So 3 to 2 via 2 plus 2 to 0. So this is infinite, 3 to 0. And 3 to 2 is, I think it's a 2 plus 2 to 0, it's a 3. So it's a 5 is better value, so we are updating 5. And the last one we are calculating is 3 to 1. So we have two ways, 3 to 2 plus 2 to 1. So now what you do is 3 to 1 is infinite. I hope it is a worst value. And this is 2 and this is 1. So this is a better value, 3 we are updating. So this is via 2 is done. And the last one is that via 3 we do it. Maybe we are taking a last different color, maybe something like this. Yes, this is via 3. So whenever we do the via 3, we are getting a final matrix. So once you got the final matrix, maybe we are trying to get it the existing values of the earlier thing. Already this is copied. Second row is copied. The third row we are copying as it is. From the previous one, this one and this one we copy as it is. So this one we are copying. This, yes, yeah, this is 0 1 2 3 0 1 2 3. Of course these diagonal values are 0, and we are trying to copy these values, third row and third column, from the previous matrix which was there. So we are getting this. So 5 3 2, of course 0. This is 5 4 5. Yes. So now let me run it, the remaining part of it. So of course it is the last one. So we are trying to, it's a via 3. So first we are trying it is 0 to 1. There are two ways, that is 0 to 3 we try. And what is the next one? What is the next one? 0 to 3 and next? Hello.
3 to 1.
Yes, 3 to 1. So with this 0 to 1 is 3 and 0 to 3 is 5. That means via 3 we are trying. 3 to 1 is 3. So it is a lesser value. It is a lesser value. 3 we are updating. And the
But
next
3
one
to
we are
1 is infinite,
3 to 1. 3 to 1. 3 to 1, 5 is there now, already updated. Yeah, it was updated. Yeah, it is there. Hello.
Okay,
Sorry,
sir.
3 to 1 already 3 is updated. No, clear.
Yes, sir.
Fine. Yeah. So the next one is 0 to 2 we are trying. 0 to 2. It's a direct edge. So 0 to 3 you can try plus 3 to 2 you can try. So 0 to 2 is infinite and 0 to 3 is 5 and 3 to 2 is 2. So this is greater value. So we are bringing this 7 is here. Okay. So then after it, we are going with this place. So we are trying with it 1 to 0, 1 to 0. What are the different paths for 1 to 0? What are the different paths? Why are 3?
So
Can
1 to
anybody? Yes, 1 to 3.
3 to
Plus,
0.
yes, 3 to 0. So 1 to 0 is 2, 1 to 3 is 4, and 3 to 0 is 5. But this is a better value, and we keep it this 1 to 0 is 2. And the next one is that 1 to 2. So 1 to 2 we are trying means that 1 to 3 is there. What is the next one?
3
Why are
to
3?
2.
Yes, 3 to 2. So 1 to 2 is infinite. 1 to 3 is 4. And 3 to 2 is 2. So 6 is a better value. So that we are updating 6. And the last two cells are there. So we are having that 2 to 0. So whether it is 2 to 0 is better, we are trying that YR3, and the next one is, what is the next one?
3
YR3.
to 3 to
3 to
0.
0. Yes, 3 to 0. So here it is 3 is there. Here it is 5, 2 to 3, and 3 to 0 also 5. But this is a better value. We try to update this. And the last one we are trying is that 2 to 1. So 2 to 1 means there are two paths are there. Why are 3? 2 to
1 to
3 is there. 2 to 3. Why are 3?
okay, sir.
No.
Yes, sir.
Plus 3 to 1.
3 to 1.
Yes. So in this case, 1 is here, 5 is here, plus 3. Sorry, plus 3. So this is a better value. We are updating this value. So the final version of this matrix is this one. It covers that all, like 0 to other vertices. See that 0 to other vertices is that, so 0 to 1 is 3, 0 to 2 is 7, 0 to 3 is 5, which is the shortest one, which is what you can say, all pair shortest. What you can say is, from the one other vertices, if you consider 1 to 0 is 2, 1 to 2 is 6, 1 to 3 is 3. So that's what we are getting is. So the final result what we are getting is this. It will show you that all pair shortest path. So here one thing you should understand is, the interesting thing which I talked about in this code is, the important coding part is, here it is. See, look at here. The minimum, what we are trying is, the minimum of I to j we are calculating. So this is the previous version of matrix. See, current version of matrix, if you want to calculate, means previous version of matrix we are using. Am I right or wrong? How do you get the previous version values? If the kth matrix you are calculating, the previous version means k minus 1 or not. Is it right? Is it right? So that's what they did it. The kth version they are calculating by getting either a direct edge from I to k, or I to k minus 1, k minus 1 to j. But the last k minus 1 is there, no? That is the kth version. So what I want to tell you is, so here, please look at here. So if I want to calculate, so this is what it is, a simple kind of a mathematical or simple kind of formula of representation. The shortest path of k we are calculating. This is the kth version of this I and j. We are calculating means, what you're supposed to do is, the minimum of the shortest path of k minus 1, that is I to j, either it is a direct, or this matrix k minus 1, the previous version, that is from I to k, or plus shortest path of k minus 1, always previous version only we are using as a reference. So K to J. This is what the complete one. So here it's a three-dimensional matrix. That's the reason they are using current version of K is calculated with previous versions of K minus 1s. That is I to J direct path we are getting minimum, or I to K minus 1, or K minus 1 to J. So the previous already via 2, via 3, via. So already second version copy we are bringing into third version. Third version copy we are bringing into fourth version. So that we are calculating via that particular matrix. So that's the reason the results you are getting is multiple rows and multiple columns. The reason is that each vertex, 0th vertex to other vertices, first vertex to other vertices, second vertex to other vertices. So that is called all pair shortest path. Here also infinite calculation is same. Only thing is multiple versions of matrix is calculated. So please look at here whenever we are applying uh, this multi-source Floyd Warshall, always even you are using adjacency matrix or adjacency list, definitely complexity is that of n cube only. The reason is that the three ways of loops we are using, that the first version of the loop to maintain the versions, second version is source, third version is destination. So every time we are taking the outer loop for the previous version of matrix we are bringing, and we are trying to find out via k, via k, via k. That's the reason every time entire matrix has to be updated uh, to update the values, the previous versions we are bringing. So even you try with adjacency matrix or adjacency list, the complexity is same. So this is because even two more algorithms are there. Actually, we are running out of time because even I spend the time now on spanning trees, it doesn't make a sense. So I will give the directions to that tomorrow TA session. Possibly they'll start with spanning trees first, then only they'll jump it into the PYQ questions. Is it okay? Any clarifications from your side? Please let me know. So one more time, I'm telling you, the graph algorithms are complex algorithms. Don't try to by heart the code. If you are trying to remember the code, it is very much difficult. First, you try to understand the concept in terms of a graph and how this adjacency matrix is creating, how this traversal result is creating. First, you try to understand, then you refer your code. So, hope you understand that. Two more algorithms are there, but we cannot spend the time more on this because we are running out of time. Tomorrow, two shortest algorithms. I think it doesn't take more than half an hour. I'll give the directions to the TA. Is it okay?
Yes.
Yeah. Any clarification from your side? Please let me know.
Sir,
Hmm.
I didn't understand that K wala part.
Hmm.
Like, what is K initially?
Yeah, K is the first matrix. First matrix we are bringing. See, this version of the matrix is there, no? Zero is
Sir, I
matrix. Hmm.
understood K is that via.
Hmm.
What
Hmm.
is from which row?
Earlier matrix values we are using the current values. Is it right?
Sir, earlier for SP1, earlier and
SP1 is using SP0 values. Is it right?
so only for first row and first column, right?
Yes, it is bringing and putting, but again the entire matrix calculation has to be done it or not.
Yes, sir.
So
Yeah.
that this time also we are running that n into n cross times. Is it right?
Sir, we are n minus
No,
1.
no, 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 no. Here, this particular calculation has to be done n into n times. Sorry, is it right?
Yes, sir.
So again, this version you are bringing, again you are trying here is n into n at almost n into n. Some calculations maybe you are copying as it is, no issue. Is it right?
Yes, sir.
So this particular version, how do you get the previous version of values? Some matrix is already there, no? Clear?
Yes, sir.
So how can you get the previous values? Please look at here, the code. Yes, here. See, look at here. Please look at here. the matrix it contains that rows and columns, 3 tuple value they're maintaining. So 3 tuple value means what it contains, that it contains a shape of the rows and columns, and one more, the number of versions are maintained. First version, second version, n number
Yes.
of dimensions. N number of dimensions. What you can say is just simply a toy diagram. If I draw, what happens? If 4 vertices are there, first version is here, second version is here. Am I right or wrong? Third version is here. Am I right or wrong?
Sir, what is
Multiple. No. See, look at here. This is rows and columns are clear.
Yes, sir.
Clear? Fine.
Yes, sir.
So here, maybe you have a matrix called 2 cross 2.
Yes, sir.
Maybe like this, 2 cross 2. This is 2 cross 2. Clear?
Sir,
No,
this.
2 cross 2. Is it 2 cross 2? Sorry, I'm sorry. It's a 3 cross 2.
Yes, sir.
Fine. 3
Yes.
rows and 2 columns. Now I did it additionally. One more thing. What happens? This 3 cross 2 matrix, another 3 copies are maintained.
Yes, sir. Yes, sir.
That
Understood.
is clear. Simple
Okay.
toy diagram. Okay.
Okay.
Yeah,
So
yeah.
K is
Third dimension.
third
First version, second version, third version.
Okay.
Recent version is using previous version values.
Okay, sir.
Okay. Yeah.
So for first value, K must
Yeah.
be 0.
Yes. The first values we are putting is that
Yeah.
infinite values this one.
Yes. Understood, sir.
Yes. Go on. So because initially we are filling the graph with all infinite. Whenever there is a path existed, we are trying to update the weight. If not there, it is direct edge is there, means we are putting it is edge weight. If indirect wedge is there, we are putting is infinite. That's it. No particular path is existed. Yeah. So I think it's okay. So any clarifications further? One more time. Don't think it is complex kind of algorithms. Only thing is just revising and recapping and just review it, YouTube streaming or earlier kind of recorded videos. Just one more time if you listen it, so you can easily come up with it. And don't consider the time complexities here. That is what one thing you should understand. Only the approach of the solving is important. And one more thing is, in the quiz examination, we never ask you the coding part of this graph algorithms. Always we'll ask you the properties of algorithms. If it is multi-source shortest path, what is the suitable algorithm? If negative weights are there, which algorithm you choose it? If negative cycles are there, which is suitable one? So this is what the things we are trying to ask in the case of that. And most questions 4th and 5th week is that actually all of them are equal weightage, because I don't want to tell you 1 to 4 weeks are equal weightage. Even in the quiz 2, if you go, all 1 to 8 weeks are equal weightage. Don't think that when it comes to the quiz 2, I need not focus on week 1 to 4. No. If quiz 1 is there, 1 to 4 is okay. If quiz 2 is there, 1 to 8 you have to you're conceptually you're strong, and little bit of coding part, because coding questions are not there in the quiz examination. OPP is meant for that coding. So hope you understand the core idea of all these. Is it clear?
Yes.
Fine. I will push this particular video recorded. I think video is generated at least by tomorrow morning. As and when we got it, we'll push this one into YouTube, and I put this one in the discourse calendar below link. I'll put this week 5 because it is not live streamable. Is it okay? Yeah. So thank you. Okay. So I'm closing the session. Thanks a lot. Have a nice day.
Sir,
Yeah. Tell me.
can we use cycle graph in Digixter?
Yeah, cycling is not a problem, because always we fix that. See, here cycling is not at all a problem in any algorithms. In any algorithm, see, in any algorithm, see, maybe cycle is existed, no issue. Sorry.
Okay.
Is it cycle is there? No issue.
Okay. Because
Dijkstra's, Belmont Ford, these things doesn't worry about the cycling. They worry about negative weights.
Yes, sir.
If negative weights are there, please careful. That's it. Cycle is there, no problem. Because we try to start it from here, and then we try to identify the all shortest path. That's it. If cycle is there also, it doesn't create any problem, because always here it contains zero, no? Source vertex.
Yes, sir.
Fine, no issue. Yeah, but only negative cycles doesn't stabilize your values. They should careful about it. Okay, yeah. So thanks a lot.
Thank you, sir.
Yeah, okay, then have a nice day. Bye bye.
Thank you, sir.
Vicky.